Hi everyone, welcome to my best ever all-in-one Edexcel IGCSE video. I am so excited to share this with you. I'm going to take you through in just the right amount of detail you'll need for your exam, as well as showing you past paper questions to help you perfect your exam technique to make your dream grade a totally achievable goal. I hope you see that this has been time extremely well spent. I'm super proud of this video and I hope you enjoy it. Just to introduce myself, my name's Hazel, I'm Science with Hazel. I studied at St John's College, the University of Cambridge. I'm a qualified secondary science teacher and I've been working as a private tutor for over 10 years, so I think I'm well placed to make this content. Throughout you'll see snippets of my revision guide. If you'd like to get hold of a copy, that's available on my website, SwH Learning. There's information there about private tuition if you want help from me or any of our tutors, as well as if you want to sign up to our online revision courses which are held on Zoom that will give you the exam preparation you need to fully ace your exams. But let's just get going. Let's start with the states of matter topics. So there are 3 states of matter: solids, liquids and gases. You need to be able to draw particle diagrams showing the arrangement of particles in solids, liquids and gases. You also need to be able to describe them. So in solids, you'll find that the particles are arranged in a regular arrangement. They're held in fixed positions and the particles are held together by strong forces. The particles have little kinetic energy. Now in liquids, those particles will be more widely spaced. They'll be mostly touching with some gaps and the particles will be able to slide over each other. The particles are held together by medium, moderate sized forces and they have a moderate amount of kinetic energy. In gases, you'll find the particles very widely spaced. They have lots of kinetic energy, which means that they're able to move quickly and randomly. There are weak forces between the particles, and the particles collide with each other and the sides of the container. It's possible to change between the various states of matter. So if you have a solid turning into a liquid, think about that, it's melting. If you've got a liquid turning into a solid, it's freezing. A liquid turning into a gas is either boiling or evaporation. A gas turning into a liquid is condensing, and then sometimes, but rarely, you get solids turning directly into a gas, and we call this process sublimation. And the group 7 element iodine is famous for undergoing sublimation. It turns directly from a grey solid to a purple vapour. Now particles may move from one area to another area by diffusion. Your definition of diffusion is the net movement of particles from an area of high concentration to an area of low concentration. This is a passive process which occurs down the concentration gradient and doesn't require energy. You can experimentally demonstrate diffusion through the use of ammonia and hydrochloric acid. So you have 2 cotton wool balls, one soaked with ammonia, one soaked with hydrochloric acid. These gases start to diffuse towards each other, and then when they meet each other, they react to form ammonium chloride, which you'll see as a solid white ring. Now the fact that that solid white ring forms so much closer to the hydrochloric acid end tells us that ammonia diffuses faster. It has gotten further in a given time, and the reason for that is because if we consider their individual MRs, we'll look at MR a lot when we study mole calculations. Ammonia has an MR of 17, hydrochloric acid has an MR of 36.5. Ammonia being much lighter will therefore diffuse far more quickly. Potassium permanganate is a purple solid that is soluble in water. A crystal of potassium permanganate is placed in a beaker containing water. After a short time, the crystal becomes smaller and the liquid at the bottom of the beaker becomes purple. Which statement explains this observation? The crystal condenses in the water. That makes no sense. Condensation is when a gas turns into a liquid. The crystal dissolves in the water. That makes sense. The crystal evaporates in the water. No, it doesn't turn into a gas. The crystal melts in the water. Well, you haven't heated it, so no. The answer is B. The beaker is left until there is no further change in the appearance of the liquid. Which statement describes the final appearance of the liquid? All of the liquid is purple. That's true. None of the liquid is purple. That's false. Only the bottom half of the liquid is purple. Nope. Only the top of the liquid is purple. And the reason why it's all purple is because the process which has occurred is diffusion, which is the movement from an area of high concentration to an area of low concentration. Remember, that is a passive process. The formula of potassium permanganate is KMnO4. How many different elements are there in potassium permanganate? So every new capital letter counts as a new element. So to highlight 1 element, 2, 3, the answer is 3. You can use your periodic table to cross-check it. Elements, compounds and mixtures. So starting with our definition of an element is a substance which contains only one type of atom. So all the elements of the periodic table, if we consider potassium just consists of potassium atoms, magnesium only consists of magnesium atoms. Elements cannot be split by any chemical means. A compound is a substance made up of 2 or more elements chemically combined, and it is crucial that you include the fact that it's chemically combined. This changes the entire property of the substance. For example, sodium is a metal, chlorine is a green gas, but when they form the compound sodium chloride, you end up with a white solid known as table salt that we sprinkle on our chips. A mixture is made up of 2 or more elements not chemically combined. A pure substance consists of only one type of material, so you could have a pure element consisting of only sulfur atoms. You could have pure water consisting of only water molecules. You can identify whether a substance is pure or not based on its melting and boiling points. They should melt and boil at a fixed temperature. If it is melting or boiling over a range of temperatures, then you don't have a pure substance. For example, pure water will boil at 100 degrees and melt at 0 degrees. Separation techniques. So how are we separating a variety of mixtures? Well, the first method is filtration. I'm just going to summarize them here. That's used to separate an insoluble solute, so one which doesn't dissolve, from a solvent. Then you've got simple distillation, which separates this time a soluble solute from a solvent. So look at these words. We've got an insoluble solute for filtration, so that could be the insoluble sand being separated from water. Simple distillation is used to separate soluble solutes, so that could be salt from water. So they're going to clearly need different methods. You've got fractional distillation. This separates liquids of different boiling points. The most famous fractional distillation example you'll come across is the fractional distillation of crude oil. And chromatography now. It's a very different separation technique. It's used to separate dyes or inks or food colourings, and the key thing here is they have different solubilities. Now, evaporation can also be used to separate soluble from a solvent, and I'll go through the slight differences here in their use when we go through these examples. So starting with filtration, these pages are taken from my revision guide. As we've said, filtration is used to separate an insoluble solute from a solvent. So that could be sand and water. It's the simplest separation technique. Just have a look here. You could be asked to draw this. You need a funnel which contains filter paper. You pour through your mixture of your insoluble solute and your solvent. So that could be sand and water. Clearly the sand stays behind in the filter paper. This is known as your residue. The water passes through to the beaker below, and in this way we've separated the two. Your water is given a specific name of filtrate. We can use evaporation in order to separate a soluble solute from a solvent. So that could be your salt again, sodium chloride. We're using evaporation here to separate it from water. So in this setup, you're going to have a tripod. Try and draw your diagrams in chemistry in 2D. You don't want to be too artistic when it comes to the Bunsen burner. An upward pointing arrow with the word heat is perfectly fine. You place your evaporating basin containing your solution on top of the tripod with a gauze in between. You gently heat, and what that will do is it will evaporate some of the water, leaving behind your hydrated salt crystals behind. Leave those to cool and you'll have salt in your evaporating basin and the water will have gone into the atmosphere. We can use simple distillation in order to separate seawater and pure water. So it looks quite complicated, but I'll just explain what's going on. Our round bottom flask here contains our mixture of salt water and pure water. We're placing that on a gauze again with a heat source from our Bunsen burner. What's going to happen here is the water, the pure water, will boil, and as it turns into a gas, it passes along this condenser, which has a stream of cold water running around it. What that cold water does is it lowers the temperature of the vapour within the condenser, causing it to turn back to liquid water. So over here on the right hand side, we've collected pure water and we've left behind the salt. Fractional distillation is used to separate liquids of different boiling points. I mentioned crude oil before. Here we have an example involving ethanol and water. Ethanol has a boiling point of 78 degrees. Water has a boiling point of 100 degrees. So clearly, when you apply heat, the ethanol will boil first. It passes up the fractionating column, down the condenser. Again, you've got a cold water stream, and it will cause that ethanol to turn back into a liquid, which can be collected in this beaker. Water with a higher boiling point is left behind. Now, chromatography is an important separation technique, and it's used to separate inks, dyes, food colorants, etc. of different solubilities. They could ask you to describe a detailed method as to how we're setting up what's known as the chromatogram, so I just want to point a few things out to you. First of all, we're going to have either a glass rod or a pencil, which we're overlaying with filter paper or chromatography paper. You need a reference line or our start line, and that needs to be drawn in pencil. It's very, very important that that pencil is used because it's insoluble. You don't want to be using ink, because when you dip the filter paper in the solvent, it will start to run and interfere with your results. You then place the inks you're interested in on the reference line. Dip your paper into the solvent and make sure that the reference line is above the solvent. Again, it will start running too quickly if that solvent is too high. Good solvents include water or ethanol. Over time, as long as those inks are soluble, they'll start moving up the paper, and the RF value can be calculated. It's the distance travelled by the component divided by the distance travelled by the solvent. In the exam, you would use your ruler to find this distance here. That would be your distance moved by the solvent, and then measure, if it was spot C they were asking you about, measure this distance, make sure it's from that pencil line. If the spot remains on the pencil line, you can infer that it is insoluble, so you might want to try a different solvent. Just a few key points. If they ask you what the stationary phase is, it's actually the paper. The mobile phase is the solvent. And then how can we use a chromatogram to identify unknown dyes in food colouring? Well, we add those dyes to the chromatography paper, we calculate the RF value, and then we compare those RF values with ones of known dyes. And just to show you again from my revision guide, if you want to write down a method as to how to carry it out, there you go. The student uses this apparatus to investigate the colours in 4 different inks, A, B, C and D. Explain 2 mistakes the student made when setting up this experiment. I can see straight away that baseline's been drawn in ink, it should have been drawn in pencil, and that water line is too high. It needs to be below the dots, so around here. So I've corrected that. So we need to explain it. Baseline should have been drawn in pencil because pencil is insoluble. You don't want that line interfering with your results. Our second mistake is that the water line is too high, and therefore the inks will mix with the water. Another student does the experiment but does not make any mistakes. The diagram shows her results. State how many colours ink D contains. Count the number of dots for D. You can see it's 3. State which of the inks tested could be mixed together to make ink D. Clearly we need ink dots at the same height, so it's A and B. Explain which of the inks tested is insoluble in water. We can see straight away that that's C, as the ink did not move. Atomic structure. So we need to first of all describe what an atom is. It's the smallest particle of a chemical element that can exist. If we were to combine two atoms, this can be of the same element or different elements, then you'll have a molecule. If we look closely at the structure of the atom, at IGCSE level, you'll need to know that it has a nucleus, which is the central part of the atom. This contains the protons and neutrons. Surrounding the nucleus of the atom are shells of electrons. They're very interested in asking about both the charge and mass of subatomic particles. So these are the neutrons, protons, and electrons found within an atom. A proton has a charge of +1. A neutron, use the name to help guide you here, is neutral, so it has no charge. Electrons have a -1 charge. Because an atom is neutral, we can therefore infer that it has an equal number of protons and electrons. In terms of the relative mass of these subatomic particles, protons have a mass of 1, neutrons have a mass of 1, and electrons have a tiny mass. So if you consider the mass number of an atom, it is comprised of the sum of the protons and the neutrons. The electrons are irrelevant here because they have such a low mass. The mass number is very tightly linked with the nucleon number. This is the number of particles found within the nucleus of the atom. So those particles are going to be the protons and neutrons. So actually the nucleon number is the same as the mass number. Now the atomic number refers to the proton number of an element. As soon as the atomic number changes, the proton number changes, you have a new element. If we look at the chemical symbol for the element fluorine as an example, the top number refers to the mass number, which remember we said is the total number of protons and neutrons. The bottom number refers to the atomic number, which is the number of protons. So in terms of calculating the neutron number, you need to do the mass number, take away the atomic number. What is an isotope? Well, it's atoms of the same element with the same number of protons but a different number of neutrons. And if we use slightly different terminology, we can say that an isotope is atoms of the same element with the same atomic number but different mass number, and that's due to the addition of extra neutrons. You'll commonly be asked to find the relative abundance of isotopes. So find the relative abundance of an isotope containing 75% of chlorine 35 and 25% of chlorine 37. So the way you do this is you take the percentage of the first isotope, multiply it by its mass number, add it to the percentage of the second isotope multiplied by its mass number, divide by 100, and you'll get a value of 35.5, which makes sense because it sits somewhere between the two isotopes' masses. The relative atomic mass now, the AR, refers to the ratio of the average mass of one atom of an element compared with 1/12 of the mass of an atom of carbon-12. As we look at the periodic table, we can see that most of the elements are metals. So what are the various physical properties of metals? Well, they're both malleable and ductile. Malleable refers to their ability to be hammered into shape. Ductile means they can be drawn into a wire. Metals tend to be shiny, sonorous, that means they make a clanging sound when you hit them. They're good conductors of heat and electricity. In terms of their chemical properties, they form basic oxides, they partake in ionic bonding, which we'll look at shortly, and they form positive ions in ionic compounds. That means that they lose electrons in order to form positive ions. Non-metals now, they form the right-hand side of the periodic table. They tend to be brittle, which means that when you hit them, they break apart. They're poor conductors of heat and electricity. They form acidic oxides and they form negative ions in ionic compounds. That means they gain electrons in order to gain a full outer shell. Non-metals can partake in both ionic and covalent bonding. So here's the all-important periodic table of elements. It shows the metals on the left-hand side. The vast majority of elements are metals. And then there's a step line coming down here, which divides the metals from the non-metals. So let's familiarize yourself with what the periodic table can tell you. First of all, make sure you use the key. There's no point learning this off by heart when they'll provide you with a key. The top number refers to the relative atomic mass. So remember, we said that that is the total number of protons and neutrons in an atom. Then you have the element symbol, such as this C here, which stands for carbon. And then the bottom number is the atomic number. And they've even kindly told you that it's referring to the proton number. So obviously no need to remember that. Elements are arranged in order of atomic number. in order of proton number. So if you check along the periodic table, along the rows, you can see that they are indeed arranged in order of atomic number. If we look more closely now at electrons, remember I taught you that atoms are neutral, which means by definition they have equal number of electrons and protons. So if we take magnesium as an example, we can see it has 12 protons, which means, according to what I just wrote, it means it has 12 electrons. If we were to draw how these electrons are arranged in the shells surrounding the nucleus, we'll label our nucleus magnesium, and then our shells are shown as concentric circles. There's just a couple of rules you have to learn, which is that the first shell can contain a maximum of 2 electrons, and then after that 8 electrons can be accommodated. So we tend to arrange them like this in pairs, keeping them nice and neat. So I'm up to 10 electrons, which means I need one final shell that shows the final 2 electrons. We can also write the electronic configuration for magnesium as 282, 2 electrons in the first shell, 8 electrons in the second shell, 2 electrons in the third shell. One thing to be aware of is these columns, these vertical columns here, are known as groups, and they're actually labelled here, group 1, group 2, 3, 4, 5, 6, 7 and 0, and actually the group number corresponds to the number of electrons in the outer shell. To show that this works, if we take magnesium again, it's in group 2, which means it has 2 electrons in its outer shell. Sure enough, if you look at my electronic configurations, yes indeed it has 2 electrons in its outer shell, and this will remain true for all the elements in these various groups. We also like to name the groups. So group 1 is known as the alkali metals, group 2 is the alkali earth metals. These elements in the centre of the periodic table are known as the transition metals. They don't have a group number. They could ask you about group 7 here, which we call the halogens, and then group 0 over here, which we call the noble gases. It's worth knowing that the noble gases have full outer shells. So let me show you what that means. If we were to take neon, which has 10 protons according to the periodic table, which means it has 10 electrons, let's draw the electronic configuration. It's 2,8. Sure enough, there's its full outer shell. What about argon? Argon has 18 protons, which means it has 18 electrons. Write that electronic configuration again. And again, argon has a full outer shell with 8 electrons in its outer shell. And this is actually why noble gases are so unreactive, because they have full outer shells of electrons. The horizontal rows now, these are known as periods. Elements in the same period have the same number of shells of electrons. So if we take sodium here, it's in the same period as magnesium. Sodium has 11 protons, which means it has 11 electrons in the neutral atom. There's its electronic configuration, 281, and sure enough, because sodium and magnesium are in the same period, they're in the same row, they have the same number of shells of electrons. They both have 3 shells, 1, 2, 3, 1, 2, 3, 1, 2, 3. The diagram shows part of the periodic table with elements represented by the letters L, M, Q, R, and T. The letters in the diagram represent elements, but not their chemical symbols. Give the letter from the diagram that represents a noble gas. Noble gases, remember, refers to group 0, which is this group down here, so we can see that it's T. The elements L and M are in the same group. State why they have similar chemical reactions. That's because they have the same number of electrons in the outer shell. Because they're in group 1, that will be 1. An atom of element Q has 31 protons. Use this information to explain how you can determine the number of protons in an atom of element R. So this is Q, it has 31 protons. As you move along the periods, so along the row, they increase in their number of protons. So R is 2 places over, so we can add 2 protons, so that's 33. The diagram shows an atom of an element. What is the name of the particle labelled? Why? Because it has a positive charge, I know it's a proton. Give the mass number of this atom. This is the total number of neutrons and protons which are found within the nucleus. So count up the particles: 1, 2, 3, 4, 5, 6, 7. Name this element. Use the periodic table on page 2 to help you. So the element is dictated by its proton number. Let's just have a look. How many protons does it have? It has 3 protons. Use the key here to help you. The proton number is the bottom number, so which element has 3 protons? We can see it's lithium. There are 2 isotopes of this element. Give one way in terms of subatomic particles that these isotopes are the same, and one way that they are different. So actually it wants your isotope definition in terms of protons and neutrons rather than atomic number, mass number. So they're the same in that they have the same number of protons. They're different in that they have a different number of neutrons. A key part of the chemistry exam is knowing how to balance equations, and what that really means is ensuring that you have the same number of magnesium and oxygen atoms on each side of the equation. The arrow here separates the left and right hand side of the equation. So we'll look at this one as a first example. You can either eyeball it, which is just have a little look, count them up in your head, and add large numbers to the front of the formulae to balance. However, some people prefer a method, so I'll show you a method right now. You want to do a vertical line separating the left and right hand side of your equation, so directly beneath the arrow. Next up, list the elements you've got on the left and right sides of the equation. Obviously these should be the same. Make sure you line them up. Now we're going to tally chart how many of each element we have on each side of the equation. So we've only got 1 magnesium. This 2 here represents the fact we've got 2 oxygens. What about the right hand side? We've got 1 magnesium and 1 oxygen. So if you sit back and compare, yes, the magnesiums are balanced, but the oxygen is not balanced. As I've said, you need to add large numbers to the front of the formulae. That's the only thing you're allowed to do when balancing equations. So we're going to add a 2 here. Now adjust. That 2 applies to everything in the formula, so it means we now have 2 magnesiums and 2 oxygens. So at this point, sit back, the oxygens are balanced, but now we've got 1 magnesium on the left-hand side, 2 on the right, so it makes sense, therefore, to add a large 2 in front of this magnesium. Adjust, so we're going to add a further point there to our tally chart, and as you can see, we're now balanced. We have 2 magnesium and 2 oxygens on each side of the equation, so this equation is balanced. Let's take a more difficult example now. In this equation, we've got sulfuric acid reacting with potassium hydroxide to form potassium sulfate and water. Let's start by drawing a dotted line to separate the left and right sides of the equation. Now list the elements. We've got far more elements in this example. Now list them on the right hand side. Do make sure that they line up left and right, or make it easier to compare. So how many hydrogens do we have on the left hand side? Well, we've got 2 here, 1 here, so that's 3. How many sulfurs? 1. How many oxygens? 4 plus 1 is 5. How many potassiums? That's 1. What about the right hand side? Well, we've got 2 potassiums, 1 sulfur, 4 plus 1, that's 5 oxygens, and 2 hydrogens. So where are there issues? Well, sulfur's okay, oxygen's okay. We've got issues with our hydrogen and our potassium. So the thing I'm going to start by doing is adding a 2 here in front of the KOH. Then I'm going to adjust. I now have 2 potassiums on the left-hand side. I've got 4 plus 2 oxygens on the left-hand side, so that's 6. Count our hydrogens. That 2 applies to everything, so we've got 2 hydrogens. 2 there, that's 4. So although the potassiums are okay, the sulfurs are okay, our hydrogens are not balanced. So I'm going to add a 2 here and adjust. That 2 now means that I have 4 hydrogens. I have 2 oxygens here, 4 over here, so that's 6. And actually, as you look at that, you can see that the whole equation is now balanced. Mole calculations. First of all, what is a mole? A mole is the amount of substance that contains the same number of units as the number of carbon atoms in 12 grams of carbon-12. Please don't worry about that. They need to pick an element to act as a reference element. They use carbon-12. So a mole is the amount of substance that contains the same number of units as the number of carbon atoms in 12 grams of carbon-12. I promise this will become so much more straightforward when we look at some mole calculations. Avogadro's constant is the number of particles present in 1 mole. And it's a very exact number. It's equal to 6.02 times 10 to the 23, so it's a very large number. You'll need to use this formula constantly in this topic, which states that mass equals the mass of 1 mole, so that's the MR, times the number of moles. And for me, it's far more straightforward if you turn that into a formula triangle, which you constantly refer to, which has mass at the top, MR, and number of moles. And the great thing about formula triangles is that you can find out different things from one formula triangle. So as we know, if we want to find mass, we can see that it's MR times the number of moles. If we want to find the number of moles, then we can see that it's mass divided by MR. Let's go through some examples of mole calculations. We'll start nice and straightforward, and then they will get slightly trickier. So the first thing we're being asked to find here is the MR of magnesium carbonate. All that means is find the individual masses of the elements contained within magnesium carbonate using your periodic table and add them up. So here's our periodic table. Do use the key, it's the top number we're interested in, so we need the number for magnesium, carbon and oxygen. So magnesium was 24, carbon was 12, we've got 3 oxygens, so we need to do 3 times 16, and then when you've totaled them up, you'll get a value of 84. So we just need to add up the individual masses of the elements in order to find the MR. Now we're being asked to find the number of moles in 54 grams of water. Here's the formula triangle I mentioned. It's so useful to write this down every single time you have a mole calculation. We're being asked to find the number of moles, so cover what you're after, it's N. So number of moles equals mass divided by MR. The mass we've been told is 54. What is the MR of water? Well, water is H2O, so we need the masses of the hydrogen and the oxygen, which is 1 and 16. We've got 2 lots of hydrogen, so 2 times 1 plus 1 oxygen. Put that into your calculator and you'll get 3 moles as your answer. In example 5, we're being asked to find the mass of 0.2 moles of calcium carbonate. Again, use your formula triangle with after mass, so we can see that's MR times number of moles. What is the MR of calcium carbonate? CaCO3. We need calcium, carbon and oxygen. So that's 40 plus 12 plus 3 oxygens. And then we want to multiply that by our number of moles, which we've been told is 0.2. So our final answer here is 20 grams. Sometimes they ask you to find the percentage by mass of an element in a compound. So you need to remember this equation, which is that you do the total mass of the element divided by the mass of the compound times by 100. So in this particular example, we're being asked to find the mass of magnesium in magnesium oxide. It is in effect the mass of magnesium divided by the mass of magnesium oxide times by 100. Use your periodic table to find that the mass of magnesium is 24. The mass of magnesium oxide is 40 times by 100 to get a value of 60%. Reacting mass calculations now. You'll be given the mass of one substance and you'll be asked to find the mass of another one. 4.5 grams of hydrochloric acid react with calcium hydroxide. Calculate the mass of calcium chloride formed. I always prefer to use a table to do this. So lay out your answers like this. Here's my formula triangle. Start by putting in the information they've given us in the question. So we know we have 4.5 grams of hydrochloric acid, so I'm going to put that there. We're being asked to find the mass of calcium chloride formed, so I'm going to put my X here. The MRs, remember, you can calculate using the periodic table. Just be careful here. Don't include the large number. We'll deal with that later. You're just adding up the individual masses of the hydrogen and the chlorine to give you 36.5 here. 40 plus 35.5 times 2 is 111 for the MR of calcium chloride. The table now tells you that you need to find the number of moles because after all there's a blank there. We can see that the number of moles is calculated by doing mass divided by MR. So that's 4.5 divided by 36.5 to give us a number of moles of 0.123287. Don't round that number too strongly because it is a very small number and you'll introduce rounding errors. You now need to find the number of moles of calcium chloride. Because of the way in which the various elements relate to each other in the equation, you can actually carry this number across as long as you check the mole connection first of all. And that just means looking at the large numbers in front of each formula. Because there's a 2 here and a 1 here, it means that rather than just stealing that number, you need to halve it. And now you're so close, you've got your MR, you've got your number of moles. So to find the mass, you do the MR multiplied by the number of moles. So multiply those two numbers together to get a final answer of 6.84 grams. Another type of mole calculation you could be asked about is determining excess and limiting reagents. Now, there's no way of guaranteeing that you have the exact amount of your reactants in order to fully react to produce your products. You will always find that one is in excess, so in plentiful supply, and one which is limiting, which actually reduces how much product can be made. People don't like these calculations, but I'm going to show you the most straightforward way of doing this. So here we have 3.2 grams of copper reacting with 0.4 moles of nitric acid. Work out which reagent is limiting and which one is in excess. The first thing you want to do is make sure you've copied down the balance symbol equation so you can use it. Set yourself up with that table as usual. Here's the all-important formula triangle. Now, the easiest thing to do here is cross out one of the numbers they give you and label it X. It will become clear why we're doing this slightly later on. It doesn't matter which one you cross out. I'm going to cross out this one and call that X. So it's going to give me something to find in my table. Now pop in the information provided in the question into your table. So we know we have 3.2 grams of copper. My X is the number of moles of nitric acid. So I'm going to put that there. Our MR, remember, we find that out using the periodic table. So for copper, it's 63.5. Our next step is to find the number of moles of copper, which we can do by doing mass divided by MR, which is 3.2 divided by 63.5. So that gives us 0.05 moles of copper. Check the mole connection. It's 1 to 4. So in order to find the number of moles of nitric acid, simply multiply that number by 4 to get 0.2 moles. So what we have done, sit back and check, what we have done is we have worked out how many moles of nitric acid we needed to react with 3.2 grams of copper. And the answer is 0.2 moles. If you check the wording of the question now, we were told that we were provided with 0.4 moles of nitric acid. So clearly, the number of moles of nitric acid is more than we require, and as such nitric acid is in excess and copper is the limiting reagent. So you will need to do some maths in order to prove that, and as I've said, the easiest way to do that is cross out one of the numbers you've been given and call it X. The next small calculation I want to show you is how we calculate the empirical formula. It's always worth remembering what the definition of the empirical formula is. It's the simplest ratio of atoms of each element present in a compound. So let's read the question. Find the empirical formula of a compound which contained 5.85 grams of potassium, 2.1 grams of nitrogen, 4.8 grams of oxygen. We're going to use a table to solve this. You want to list your element symbols at the top of your table, and then you're going to write mass, MR, and number of moles down the left-hand side as per usual. Here's your formula triangle. So now let's start entering information in from our question. So we know we've got 5.85 grams of potassium, 2.1 grams of nitrogen, and 4.8 grams of oxygen. We can now find the relative atomic mass from the periodic table. So potassium is 39, nitrogen is 14, oxygen is 16. Number of moles we do by dividing the mass by the MR. So 5.85 divided by 39 to give 0.15, 2.10 divided by 14 to give 0.15, 4.8 divided by 16 to give 0.3. The next stage, and I'm going to write the instruction here, is identify and divide all the numbers by the smallest number. So what do I mean by that? Look at your numbers you've just calculated, identify the smallest number, and divide each of those numbers by the smallest number. So clearly that is 0.15. So when you've done that, you'll get 1, 1, and 2 as your answer. And this is actually a ratio which will provide you with your final answer, because it tells you that for every potassium and nitrogen, you need 2 oxygen atoms. So your final answer actually looks like this. So do make sure you write out your empirical formula at the end. Now, a water crystallization calculation is very similar to an empirical formula calculation, and I'll show you how that works right now. So here 11.25 grams of copper sulfate, which is hydrated, so combined with water, is heated until it loses all of its water. Its new mass is found to be 7.19 grams. Calculate the value of X. I know this looks disgusting, but I'll show you how you're going to use the previous method here. Just write out your hydrated formula. Then you want to create your table, and I always just create that table around the dot. So I separate it out here. Here's my mass, my MR, my number of moles, my formula triangle. Carefully input information into your table. So I'm looking for the mass of copper sulfate. I want it on its own without water, so I know that that value there is 7.19. What is the mass of water? Well, clearly it's the difference between these two numbers, because the 11.25 contains water, the 7.19 doesn't. So put that into your calculator and you'll get a mass of 4.06. Now find the MR of copper sulfate. So that's using your periodic table as usual. 63.5 plus 32 plus 4 lots of oxygen. So 4 lots of 16 gives 159.5. The MR of water is 2 plus 16, so that's 18. Find the number of moles by doing mass divided by MR. So 7.19 divided by 159.5. Find the number of moles of water, 4.06 divided by 18. Write that same instruction to yourself as before, so divide by the smallest number. And that will give you a final ratio of 1 to 5. And it's that 5 that's important because it's actually what our X value is. So I'm hoping you can see that's very, very similar to the empirical formulae calculation we just did. Halon 1301 is a compound used in some fire extinguishers. It has a percentage composition by mass of, showed by calculation that the empirical formula is the following. So we'll use our table, list our elements. We write mass, MR, number of moles. There's our formula triangle. It's worth spending time doing this. What is our mass? Remember, because they're all proportional, you can take percentages as being your mass. Use your periodic table to find the relative atomic mass of carbon, bromine and fluorine. To find the number of moles, you just do mass divided by MR, so this number divided by this one. Do that 3 times. And then your next step is to divide by the smallest number. So obviously the smallest number along here is 0.671. So if you divide all those numbers by 0.671, you'll get 1, 1, and 3, and that's actually your ratio. So that will tell us that the empirical formula is CBrF3, which is what we're hoping for. The diagram shows the displayed formula of a molecule. Draw a dot and cross diagram to show all the outer electrons in this molecule. So we've got a covalent compound. Let's keep it nice and symmetrical. Label your elements. Carbon has 4 electrons in its outer shell. Fluorine and bromine both have 7. Just double check that they both have a full outer shell of electrons. They do. The gas burned in a Bunsen burner is methane. The equation for the complete combustion of methane is: calculate the mass of oxygen required to react with 32 grams of methane. So the most straightforward thing to do here is, in the exam, copy down your balanced symbol equation. Set yourselves up. We're being asked to find the mass of oxygen, so my X goes here. We've got 32 grams of methane. Pop in the MRs, 16. Work it out using your periodic table for oxygen. Remember, when you calculate the MR, you ignore the big number, so it's just 16 times 2, which is 32. To find the number of moles, we do mass divided by MR, 32 divided by 16, which is 2. Check the mole connection. That means look at the large numbers. It's 1 to 2, which means that we need to double this number to determine the number of moles of oxygen. And you're now ready to find its mass by doing MR times the number of moles. So that works out to be 32 times 4, which is 128. The overall equation for the formation of hydrated copper 2 sulfate crystals is this. In an experiment, a student completely reacts 9.54 grams of copper 2 oxide. Show that the maximum possible mass that can be produced is around 30 grams. Give your answer to an appropriate number of significant figures. So I'm setting myself up as usual. We have 9.54 grams of copper oxide. We're after this mass here. What are the MRs? They've told us 79.5, 249.5. Find the number of moles of copper oxide by doing mass divided by MR. So that's 9.54 divided by 79.5. Check the mole connection. It's 1 to 1. So we put that same number across there. And then find the mass by doing number of moles times the MR to get 29.94. Which is approximately 30 grams. That's great. But what is an appropriate number of significant figures? Because you've got 3 significant figures here of the copper 2 oxide, we want to match that with the other mass. So I'm going to go 29.9. In this experiment, the actual yield of the crystals is this. Calculate the percentage yield. So we do actual yield divided by theoretical yield times by 100. to get 80%. The table shows the students' results. Calculate the mass of this produced by heating. So we need to do the mass of our substance with the test tube minus the mass of the test tube to get 6.65. What is the mass of water produced? Well, it's the difference between the hydrated crystal and the anhydrous version, the one without water, to get 5.4 grams. Calculate the value of x and give your answer to the nearest whole number. So this is like a complicated empirical formulae calculation. So we write out the formula. This one is super nasty. In its hydrated version, then we put a line down where the dot is, mass MR, number of moles. We've worked out the individual masses, so we know that the mass of water is 5.4 grams, because we did that right here. The mass of the complicated salt is 6.65. The MR, we've been told, is here, so please don't do any extra working out. You won't be awarded any marks for that. We can now do the number of moles by doing mass divided by MR. And then because we want a ratio, we need to divide by the smallest number. So divide both sides by 0.0125 to get 1 to 24, and I'm really happy that's a whole number. I can be confident that's correct. Let's start with defining an ion. It's an atom which has either lost or gained electrons. If the atom has lost electrons, because the electrons are negatively charged, you get a positive ion. If an atom has gained electrons, because they're negatively charged, you gain a negative ion. Metals form positive ions. How do we work out the charge on a metal ion? Well, you need to learn the following. You need to learn that for groups 1 to 3 in the periodic table, remember the group is the vertical column. I will show you examples shortly. The charge on the ion is the same as the group number. So let's show that that works. Here's elements in group 1 to 3. Here are our vertical columns. If we were to take lithium here, I've already told you that the metals form positive ions, so lithium has a 1+ charge. If we take beryllium next door, it's in group 2, so it's going to be a 2+ charge. Aluminium over here is in group 3, it's going to be a 3+ charge. The next thing to be aware of is that non-metals form negative ions. So they gain electrons to have a full outer shell. You need to learn that for groups 5 to 7, slightly more complicated but not too much more, the charge on the ion is 8 minus the group number. So let's see what we mean by that. So non-metals form negative ions and the charge on the ion is 8 minus the group number. So we're looking at groups 5, 6 and 7. Nitrogen here is in group 5. So to find the charge on its ion, you do 8 minus the group number. So 8 minus 5 is 3. And you give it a negative sign because I told you non-metals form negative ions. What about if we look at oxygen over here? There's the chemical symbol of oxygen. What is the charge on its ion? Well, it's 8 minus its group number, so 8 minus 6 is 2, and there we are, 2 minus. Let's do the fluoride ion next door. 8 minus 7 is 1, so it's 1 minus. So you can work out the charges on these ions just using your periodic table. Annoyingly, the transition elements, because they don't have a group number, you need to learn just a few of them, but you do need to learn them off by heart because they're metals, they're going to form positive ions. So I'll start with the transition elements you need to learn off by heart. This is silver, this is copper, here's iron 2, here's iron 3. It's helpful here if they tell you which valency of iron they're interested in, because actually the number corresponds to the Roman numerals in the brackets. Zinc is Zn2+, lead is Pb2+, and then it's not a metal ion, but it's still a positive ion. This is a nasty one, but you need to learn that that is the ammonium ion. What about the negative ions you need to learn off by heart? This is what's known as the hydroxide ion. Here's the nitrate ion, carbonate, and sulfate. That's a 2. Just a word on naming. Look, these 3 ions have oxygen combined, and we refer to that as 8 in their names. So nitrogen combined with oxygen is nitrate, carbon and oxygen carbonate, sulfur and oxygen sulfate. So here are your rules for knowing what the charge is on the various ions, but how do we combine these ions in order to form the formulae? So let's do an example, calcium chloride. So let's apply what I just taught you. Calcium is right here. It's a metal, which means it's going to form a positive ion. It's in group 2, so it's just going to be Ca2+. Now the chloride ion, chlorine is over here. It's in group 7. Because it's a non-metal, it will form a negative ion. Remember, you do 8 minus the group number to work out the charge on that ion. 8 minus 7 is 1, so it's 1 minus. So here are the 2 ions you'll need. You need to have a neutral formula. So what that means is making sure you have the right number of each ion to produce a neutral formula. So you can see you've got an imbalance in charges here with a 2 plus and a 1 minus. It makes sense, therefore, that you need a second chloride ion. The way you write that to form calcium chloride is you write small numbers after the formula. So I'll do the first one for you. The formula of calcium chloride looks like this. That 2 represents the fact that you need 2 chloride ions. Let's do lead 2 oxide now. So identify your elements. Here's lead. There's the oxygen responsible for oxide. Now lead is annoying. It's a transition element, so you have to learn that it's Pb2+. There's no way of working that out from the periodic table. However, oxygen over here, it's a non-metal, so it's negatively charged. 8 minus its group number. 8 minus 6 is 2, so it's 2 minus. So that's a nice straightforward one because the charges are balanced, it's just PbO. Let's do potassium carbonate now. Potassium here, it's a metal, so it's going to have a positive charge. It's in group 1, so it's just a 1 plus charge. Carbonate is one of the annoying negative ions you need to learn off by heart, which is CO3 2 minus. So these are the 2 ions. Double check the charges. We've got 1 plus versus 2 minus. So clearly we need a second potassium ion. So we write that by writing K2CO3. Ammonium sulfide. So ammonium is one of the nasty ions. You have to learn that off by heart. It's NH4+. Sulfide. Sulfur is over here. It's a non-metal, so it'll have a negative charge. It's in group 6, so we do 8 minus 6 is 2, so it's a 2 minus charge. Check the charges. We've got 1 plus versus 2 minus, which means we need a second ammonium ion. There it is. Just be a little bit careful here. Because you need 2 of the ammonium ions, you can't just write it like that. That looks so weird. It's not NH42. You need to include a bracket to show that the 2 applies to everything, and then include the sulfide. Let's look at this one. I'm changing colour to show how horrible it is, but it's totally doable. So iron 3, it's Fe. That Roman numerals tells us that it has a 3 plus charge. The sulfate ion is one we had to learn off by heart. look, we have a 3 plus versus a 2 minus. You need to work out what number both 3 and 2 go into. It's 6. So in order to get 6 plus, we need 2 iron ions. We need 3 sulfate ions. I'll highlight them to show it really clearly for you. But you can see how these are balanced because you have 6 plus versus 6 minus. And then we need to acknowledge that by showing that we have 2 Fe's. And then we need our brackets again to show that we need 3 sulfate ions. Ionic and covalent bonding. So the first thing to be aware of is that ionic bonding occurs between metals and non-metals. Covalent bonding is non-metals only. And remember, I just said that metals form positive ions due to the fact that they lose electrons, and the non-metals in ionic bonding form negative ions because they gain electrons in order to gain a full outer shell. With covalent bonding, you're going to see what's known as a shared pair of electrons, and I'm going to show you how to do both types of bonding very shortly. But let's start with ionic bonding. So the first thing I want to do is share with you a definition for an ionic bond. So it is the electrostatic forces of attraction between oppositely charged ions. And we've already discussed where those oppositely charged ions come from. They come from a metal ion and a non-metal ion. Let's take our first example, which I'm going to pick sodium chloride. Let's double check their electronic configurations. I taught you previously how to work out those electronic configurations. So here's sodium over here. That bottom number refers to the number of protons and the number of electrons. We have 2 electrons in the first shell, 8 in the next shell, and then we fill up to make a total of 11. So sodium's electronic configuration is 281. What about chlorine? Following the same rules, it's 287. So I'm just labeling them here. We now want to draw the electronic configurations. It's up to you if you just want to draw the outer shells. There's 2 electrons in the first shell, followed by 8, followed by 1. Let's do the chlorine atom now. 287. Use dots to show that these electrons belong to a different element. There's the 7 electrons on the outer shell. That's the most important shell here. Now, when elements start bonding, what they're really trying to do is gain a full outer shell. So you need to ask yourself, how in an ionic bond will they both gain a full outer shell? And you can see that the most straightforward thing to happen here is that the sodium transfers an electron to the chlorine, just like this. And by doing so, it loses the final shell here, meaning that it has a full outer shell, because that becomes the new outer shell. And the chlorine gains an electron, giving it that all-important 8 electrons in its outer shell, meaning that it's also full. So let's draw our final answer, because this is really just your intermediate step. So here's your final answer. We've shown how sodium's lost an electron, gaining a full outer shell. We've shown how the chlorine has gained an electron, again gaining a full outer shell. You just need to include square brackets now, together with a charge. The sodium has lost an electron. Electrons are negatively charged, which means it has a positive charge. The chlorine's gained an electron, which means it now has a negative charge. So we can see here our final answer for an ionic bonding diagram showing the formation of sodium chloride. Let's take a second example now of magnesium fluoride. Start with their electronic configurations. Right, there's magnesium, there's fluorine. Magnesium has 12 electrons, so that's arranged as 282. Fluorine has 9 electrons, so that's arranged as 2.7. Let's show those electrons. 2 electrons on the first shell, 8 electrons on the second shell, 2 electrons on that final shell. What about the fluorine? Again, making sure we're using dots to represent the fact that we have a different element. 7 electrons on the outer shell for fluorine, Just be a little bit careful here. We can see how the magnesium will donate an electron to the fluorine. However, we have issues in that we don't have a full outer shell for magnesium because we've still got that spare electron there. So you have to decide what is the most sensible thing to do here. Well, it's to introduce a second fluorine atom. So here I am introducing my second fluorine atom. You can see how there's now space to accommodate another electron. So the magnesium's really happy as it's donated both of its electrons. Both of these fluorine atoms are happy because they've each gained an electron. Again, this is an intermediate step. So what does our final answer look like? Well, our final answer looks like this. The magnesium has lost its outer electrons. It's lost 2 electrons, which means it has a 2+ charge. Each of these fluoride atoms has gained an electron, which means they each have a 1- charge. So we have a magnesium ion and 2 fluoride ions. Let's look at covalent bonding now. So what is our definition of a covalent bond? It's the electrostatic forces of attraction between nuclei and shared pair of electrons. And as I said previously, it's important that you're aware that this occurs between non-metals only. You are always trying to gain a full outer shell when it comes to bonding. Let's take our first example, which is water. The formula of water is H2O. Keep everything symmetrical. So you're going to show the outer electrons. You need to draw overlapping circles to show that they're going to share electrons. Label your atoms. There's my H2O. Use your periodic table now to work out how many electrons hydrogen and oxygen have in the outer shell. We're only interested in the outer shell here. Hydrogen has 1 electron in its outer shell. Oxygen, write the electronic configuration. It's 2.6, which means it has 6 electrons in its outer shell. So we'll show the 1 electron there for each of the hydrogens. We said that oxygen has 6 electrons in its outer shell. Count them carefully. There's 1, 2, 3, 4, 5, 6. Try and keep it super neat as I've done here. So we've shown the 6 electrons for oxygen. We've shown the 1 electron for each of the hydrogens. Just check now that both atoms have a full outer shell. 2, 4, 6, 8. Yep, that oxygen's happy. The hydrogen, remember, because it only has the first shell, you only need 2 electrons in the first shell for it to be full. So that's why the hydrogen's happy with just 2 electrons. We've done our first example. What about ammonia now? Which is NH3. Keep it symmetrical again. We're going to have a central nitrogen atom surrounded by 3 hydrogens. Label them. I know straight away that the hydrogens all have 1 electron in the outer shell, so I'll label those. What about nitrogen? Here's nitrogen, has 7 electrons, which are arranged as 2.5, so it has 5 electrons in its outer shell, as corroborated by that 5 in its group number. So let's show the 5 electrons around nitrogen. 1, 2, 3, 4, 5. Now, do both atoms have a full outer shell? Hydrogen's happy, yes, it has 2 electrons in its outer shell. Double check nitrogen. 2, 4, 6, 8. Yes, it's full. So that is done. There's ammonia. Let's look at carbon dioxide now, because that's actually quite a nasty one. Carbon dioxide has the formula CO2. Now carbon is in group 4, so it has 4 electrons in its outer shell. Oxygen has 6 electrons in its outer shell because it's in group 6. How are we going to arrange those? Now it's worth learning for carbon dioxide that it actually has a double covalent bond. So what I mean by that is that you'll actually have 4 electrons in the overlap like this. It's really worth learning that to make it easier for yourself. So look, these 2 crosses I'm going to give to carbon and say that, look, 1, 2, 3, 4. There's the 4 electrons belonging to carbon. The dots, for argument's sake, I'm going to say belong to oxygen. We know we need to show 6 electrons. So we have 2 there, 3, 4, 5, 6. Do the same over here. And now double check, do we have full outer shells? Count them up for carbon. In the overlap we have 4 electrons plus 4, so that's 8. It's happy. What about oxygen? 4 in the overlap plus these 2, 8. Same is true over here, so that's actually your carbon dioxide covalent bonding diagram. The final example I want to show you is methane, CH4. Let's arrange it so that we have a central carbon atom surrounded by 4 hydrogens. Remember we said that hydrogen has 1 electron in its outer shell. We said that carbon has 4 electrons in its outer shell. Double check the periodic table if you don't believe me. But this is quite a nice straightforward one because we've shown that carbon now has 8 electrons, so it has a full outer shell. Hydrogen has 2 electrons, so it has a full outer shell, so that's done. So here are just some examples of covalent bonding. This question is about ionic compounds. State the formula of the cation and anion in magnesium sulfate. So the cation is the positive ion, the anion is the negative ion. Magnesium is in group 2. It's a metal, which means it's lost 2 electrons to form Mg2+. The sulfate ion, they're being mean there, you're going to have to learn that off by heart, it's SO4 2-. The diagram shows the electronic configuration of a potassium atom and an oxygen atom. Potassium oxide is an ionic compound. Draw the electronic configuration of a potassium ion and an oxide ion. Show the charge on each ion. So this is ionic bonding. So remember, the metal will lose an electron to gain a full outer shell, so it's going to lose this electron here. Oxygen will gain electrons to gain a full outer shell. It needs to gain 2 electrons. In terms of drawing this, so there's my potassium ion with a full outer shell. It's lost an electron, which means it's gained a 1+ charge. The oxide ion gains electrons from the potassium, so we use those dots to represent that they've come from the potassium. Because they've gained 2 electrons, it's now a 2- charge. Let's go through the chemical structures topic. So really what we're talking about here is the major differences between giant ionic structures, giant covalent structures, and simple molecular structures. Now, giant metallic structures is a paper 2 topic, but I do want to quickly tell you about the types of substances which make up the 4 structures, because it will make it so much easier for you to understand their properties. So, giant ionic structures are comprised of a metal and a non-metal. Giant covalent structures are non-metals only, and simple molecular structures are also made out of non-metals. You do need to know a little about their melting points. If they contain the term giant in their names, then it makes sense that they have high melting points. So as a result, giant covalent, giant ionic, and giant metallic structures all have high melting points. Simple molecular structures have low melting points, and they will expect you to give a really good detailed reason as to why this is the case. So let's talk more about giant ionic structures. We said that they have high melting points. We said that they're made up of metals and non-metals. So why do they have such high melting points? Well, that's due to their strong ionic bonds. Now, this is because they have strong electrostatic forces of attraction between the oppositely charged ions, which require a lot of energy to overcome. And it is important that you point out that they require a lot of energy to overcome. Giant ionic structures have an interesting property whereby they conduct when molten or in aqueous solution, but they don't conduct when solid. The reason for that is that in their solid structure, giant ionic structures like sodium chloride, for example, the ions aren't free to move. However, when they're molten or in aqueous solution, so dissolved in water, the ions are free to move. Good examples of giant ionic structures include sodium chloride, magnesium oxide. Notice they're comprised of a metal and a non-metal. Now, giant ionic structures are brittle, which means that when you hit them, they break up. And why is that? So when you apply a force, the layers of ions slide. This means that ions with the same charge may end up next to each other. The same charges repel and the structure breaks apart. Now let's distinguish between giant covalent structures and simple molecular structures, because after all, I've taught you that they're both made out of non-metals. Now, In order to actually work out whether a structure is giant covalent or simple molecular, obviously this is slightly more tricky given that they're both made up of non-metals. I recommend learning some key examples of giant covalent structures, such as diamond, graphite, and silicon dioxide. If you're told about another non-metal substance, one which is a gas, or they tell you it has a low melting point, you can therefore infer that it is a simple molecular structure. So let's talk more about giant covalent structures. The first one I want to talk to you about is diamond and graphite. Now, these are both allotropes of carbon. This means that they are both forms of carbon, but they have different structures. So starting with diamond. Now, diamond has a very high melting point. The reason for that is because it's a giant covalent structure, which means it's made up of many strong covalent bonds, which require a lot of energy to break. And you need to use this sort of language in your answers. You'll find that my revision guide is chock-a-block full of this key exam wording. You can get an extra mark if you point out in diamond that it has a giant tetrahedral structure. Tetra meaning 4. What that really means is that each carbon atom is bonded to 4 others in a giant structure which requires an awful lot of energy to break up. Graphite now, you find that the carbon atoms are arranged differently. They're arranged in layers. Again, you've got a giant covalent structure, meaning that you have many strong covalent bonds, which require a lot of energy to break. But what you find with graphite is that there are weak forces between those layers of carbon atoms, which require little energy to break. And actually that enables graphite to be used as a lubricant because those layers can slide over each other. The graphite itself is said to be slippery. Now, more differences in their structures and properties include the fact that graphite can conduct, diamond can't. The reason for that is in graphite there are delocalized electrons which are free to move and carry the charge. In diamond, no such electrons are free to move. Let's talk about simple molecular structures now. I've already said that they're made up of non-metals, they have low melting points. The reason for that is that with simple molecular structures, when you melt them, when you boil them, what you're doing is you're breaking the forces which hold the molecules together. You're not breaking apart the individual atoms. So, simple molecular structures have low melting points because they contain weak intermolecular forces. These require little energy to break, and as a result, they have a low melting point. Be prepared to explain this if they give you a specific example. Why is carbon dioxide a gas at room temperature? Identify its structure. It's a simple molecular structure. It has weak intermolecular forces, which require little energy to break. Why does sodium chloride have a high melting point? Identify its structure. Because it is a giant ionic structure. It has strong electrostatic forces of attraction between oppositely charged ions, which require lots of energy to break. You can see how I'm providing a very detailed answer here. Now there's a third allotrope of carbon you need to be aware of. So a third form of carbon. We've met graphite and diamond previously. The third allotrope is C60 fullerene, which is actually a simple molecular structure. It has a much lower melting point compared with diamond and graphite. Diamond, graphite and silicon dioxide all have giant covalent structures. The diagram shows the structures of these substances. Explain why silicon dioxide has a high melting point. So we know it's a giant covalent structure. We won't get a mark here because they've told us that. But remember, that means that they have many strong covalent bonds which require a lot of energy to break. Explain why graphite conducts electricity. Remember, graphite has delocalized electrons which are able to flow through the structure. State why diamond is hard but graphite is soft. It's all to do with the arrangement of the atoms. So remember, diamond has a giant tetrahedral structure, which means that each carbon atom is bonded to 4 others, whereas graphite atoms are arranged in layers which can slide over each other, hence why it can be used as a lubricant. The boiling point of halon 1301 is -58. Explain why it has a low boiling point. we can see that it's just made out of non-metals. So we're picking between whether it's a giant covalent structure or a simple molecular structure based on the fact it has a low boiling point. Means that we must have a simple molecular structure with weak intermolecular forces which require little energy to overcome. Group 1 metals. So we're talking about the first column in the periodic table. These metals are known as the alkali metals, and I'll explain why they're given this name very, very shortly. Now remember, all elements in the same group have the same chemical properties, and that's because they all have the same number of electrons in their outer shell. For group 1, that means that they have 1 electron in their outer shell. So what are the physical properties of the group 1 metals? Well, the group 1 metals are super unusual when compared with your more typical transition elements. First of all, they're soft, so you can actually cut them with a knife, and they have low melting and boiling points. They are shiny though, so if you cut them, they'll be shiny, but then that will slowly tarnish. Another unusual property is that they have low density, which means they float on water. So the group 1 elements are very different from your typical transition elements. The group 1 elements are incredibly reactive. That means they'll react with cold water. When you handle them, you need to first of all store them in oil to stop them react. You need to handle them with forceps because they'll actually react with the water and oils in your skin. So let's go through the group 1 elements and the various observations when they're added to cold water. We'll start with lithium, which is at the top of the group. Lithium is the least reactive group 1 element, so you'll see the least violent reaction here. First of all, see the lithium float on water. It skids across the surface of the water. There will be fizzing, and that's due to the production of hydrogen gas, and eventually that lithium will disappear. Sodium sits beneath lithium in the periodic table, therefore it's slightly more reactive. This time you might see an orange flame. You'll see more fizzing due to hydrogen gas released. The sodium will melt and eventually disappear. Potassium sits beneath sodium. This time you'll see a lilac flame. The reaction gets even more violent. You'll see stronger fizzing, so stronger effervescence. It will move faster over the surface of the water. Again, it will melt and disappear. So why are the group 1 elements known as alkali metals? Well, it's all to do with the solution that's produced when they're added to cold water. The group 1 elements produce a hydroxide, so lithium hydroxide, sodium hydroxide, potassium hydroxide. Due to the presence of that hydroxide ion, you get a very strongly alkaline solution, which when universal indicator is added to that solution, it will turn purple. Hence the name alkali metals. The alkali metals produce an alkaline solution. Let's look at an example equation. So lithium plus cold water forms lithium hydroxide and hydrogen. That hydrogen gas is responsible for the fizzing, the effervescence we see when lithium is added to cold water. Let's convert this to a balanced symbol equation. So lithium is Li, water is H2O. The formula of lithium hydroxide, lithium's in group 1, so it forms a 1 plus ion. Hydroxide ion you need to learn off by heart, it's OH minus. Because these balance, we have no issues here with writing LiOH. And then hydrogen is a diatomic molecule, meaning it consists of 2 atoms, which is why you need to write H2. Let's balance it. I'm going to show you the method here. You list your elements on the left and right hand sides of the equation. Tally chart how many you have of each element. 1 lithium, 2 hydrogens, 1 oxygen. 1 lithium, 3 hydrogens, 1 oxygen. So we have issues here clearly with the hydrogen. I need more hydrogens on the left hand side, so I'm going to add a 2. Then adjust. We now have 4 hydrogens and 2 oxygens. We don't have enough oxygens now on the right hand side, so we need to adjust. Let's put a 2 there, which means we now have 2 lithiums, 2 oxygens and 4 hydrogens in total on the right hand side. We're so close now. All we need to do now is add a number 2 in front of the lithium, and there is your balanced symbol equation. It's also possible to just eyeball it and have a look once you get familiar with doing balancing equations. That hydroxide ion here remember, is responsible for the alkali solution produced, which turns the universal indicator purple. The group 1 elements can also react with oxygen to form a metal oxide. They form ionic compounds and they can react with halogens. This question is about sodium and potassium. A trough is filled with water and a few drops of phenolphthalein indicator are added. A small piece of sodium is dropped into the water. One of the products of the reaction is an alkali. It's going to contain OH. Complete the chemical equation for the reaction of sodium with water. So first of all, we need to balance it. Count your number of hydrogens on each side of the arrow. We've got 3 on this side, 2 on this side, which means I need a 2 here. Count your number of oxygens. We now have 2 oxygens here, only 1 here, so I need a 2 here. That's bumped up my number of sodiums to 2, so I need a 2 here. So make sure you've balanced it correctly, and now you need to add state symbols. Sodium is a solid, and sodium hydroxide is an aqueous solution. Identify the ion that causes the solution to become alkaline. It's OH-, the hydroxide ion. Give 3 observations that would be made when sodium reacts with water. The sodium moves, fizzing occurs, the sodium melts. The group 7 elements are known as halogens. Now they all have the same chemical properties, and that's because they have 7 electrons in their outer shell. So if we look at group 7 more closely, we know it goes from fluorine to chlorine to bromine, iodine, astatine. They will expect you to know their state of matter and their colour at room temperature. Be aware that the melting point of these elements increases down the group. As a result, the elements at the top of the group will be gases, then we'll move to a liquid, bromine, and then down to the solids, iodine and astatine. So fluorine at the top of the group is a yellow gas at room temperature. Chlorine is a green gas. Bromine is a red-brown liquid. Iodine is a grey solid. And astatine, they'll expect you to predict that it's a black solid, because the elements also get darker in colour as you descend the group. Remember that iodine undergoes sublimation, which means it turns directly from a solid to a gas, turns directly from a grey solid to a purple vapour. Now the halogens are able to react with hydrogen to form hydrogen halides, which are highly acidic and poisonous. For example, hydrogen reacts with bromine to form hydrogen bromide. Hydrogen reacts with chlorine to form hydrogen chloride, which when dissolved in aqueous solution forms hydrochloric acid, which you'll be far more familiar with. The halogens are all diatomic molecules. That means they exist as 2 atoms combined to form a molecule. So if you're asked to write chlorine as a formula, you need to write Cl2. The same is true for the other elements. Halogens partake in displacement reactions, where a more reactive halogen displaces a less reactive halogen from its compound. Let's take the reaction of chlorine reacting with potassium bromide. Because chlorine is higher up in the group, it's more reactive. We've discussed the reasons why it's more reactive. It will displace the bromide. So you'll end up with potassium chloride and bromine. Do be prepared to state any observations. So because you're gaining bromine, you'll expect to see the solution go darker. It could actually turn orange. Let's take another reaction. Chlorine reacting with potassium iodide. Chlorine is more reactive than iodine, so it displaces the iodide. You'll form potassium chloride and iodine. You'll see a brown solution here, and you do need to be prepared to write a balanced symbol equation. The table gives information about the first 4 elements in group 7 of the periodic table. Astatine has an atomic number of 85 and is the 5th element in group 7. It is possible to make predictions about astatine by comparison with other elements in group 7. How many electrons does an atom of astatine have in its outer shell? Well, it's in group 7. That number tells you how many electrons it has in its outer shell. It's 7. What physical state and colour would you expect for astatine at room temperature? So remember, as you descend the group, they have higher melting points. So if iodine is a grey solid at room temperature, astatine must also be a solid, and it's going to get darker in colour, so I'm going to call it a black solid. Predict the formula of the compound formed between astatine and hydrogen. Suggest a name for this compound. So hydrogen is an H+ ion. Astatine, being in group 7, is At-. The positive ion always comes first, so it's going to be HAT. suggest a name. What is its name? Hydrogen. Remember, we changed the endings on the halogens, chloride, iodide, bromide, so it'd be astatide. Suggest how the reactivity of astatine compares to that of iodine. Explain your answer. So, as you descend the group, the elements become less reactive. Fluorine is the most reactive, iodine is the least reactive. So, astatine being beneath iodine, I'd expect to be less reactive. As the elements are less reactive as you descend group 7. Gases in the atmosphere topic. So first of all, what is the composition of air? Now, it's made up of 78% nitrogen, 21% oxygen, 0.04% carbon dioxide, and less than 1% of argon. If they ask you about a compound which is found in unpolluted air, you want to mention either water or carbon dioxide. Make sure you read the question carefully as to whether they're asking about a formula, an element, a name. You do need to be really careful in chemistry that you're actually answering the question being asked. How can we prove experimentally that approximately 21% of air is made up of oxygen? Well, there's quite a few different experiments. One of them involves heating copper in a silica tube positioned between two gas syringes. The idea being that as you heat the copper, you pass the air in the syringes from one side to the other. The oxygen in the air reacts with the copper being heated. It oxidizes the copper to form copper oxide, which you'll see is a black solid. At the end of the experiment, you compare the volume of air in the gas syringes before and after, and you should be able to find that approximately 21% of that air was indeed made up of oxygen because it reacted with the copper. Obviously, when you take the volumes in the gas syringe, you need to make sure that everything is cool because gases expand when they're heated. You can also use iron filings placed in a burette which is full of air in a similar way to determine the approximate percentage of oxygen in air. The end of the burette is placed in a trough of water. The iron reacts with the oxygen and water enters the burette. A third way of determining the percentage of oxygen in the air is using the element phosphorus. Here, phosphorus is placed on a tray inside a tube full of air. The tube is placed in a beaker of water. The phosphorus is lit with a hot wire. The phosphorus reacts with oxygen, meaning that the volume of air decreases. Obviously, you can't be left with a vacuum, so water enters the tube, and that raises the tray carrying the phosphorus up. As well as the reaction of copper with oxygen forming black copper oxide, there's other reactions you need to be aware of, including what happens when you burn magnesium in air. It reacts with the oxygen. You'll see a super bright white light, so you'll need to wear special safety goggles, and a white solid of magnesium oxide is formed. If you dissolve magnesium oxide in water, you'll form magnesium hydroxide, which is an alkaline solution. Universal indicator should turn blue. Hydrogen also burns in oxygen. It burns with a pale blue flame and forms water. When sulfur burns in oxygen, a blue flame is formed. Sulfur dioxide gas is formed, which is both poisonous and colourless, so you want to carry this out in a fume cupboard. That sulfur dioxide can dissolve in water to form an acidic solution of sulfurous acid. There are several different thermal decomposition reactions you need to know about. Thermal decomposition simply refers to heating a substance until it breaks apart. The heating of metal carbonate is an example of a thermal decomposition reaction. So what happens when you heat calcium carbonate? Remember, calcium carbonate is limestone. It forms calcium oxide and carbon dioxide. If they ask you about copper 2 carbonate, do be aware that copper 2 carbonate is a green solid. When it's heated, it breaks down to form copper oxide and carbon dioxide. And remember, we already said that copper oxide is a black solid. These are some really niche points on the spec, and it is part of the specification which is less well known by students, so it's a good opportunity to really boost your mark here. Air is a mixture of gases. The two main gases present are the elements nitrogen and oxygen. Another element that is present in air is, crucially, they want an element here, so be careful. Despite the fact that carbon dioxide is present in air, you don't want to pick that because it's a compound. The answer here is argon, which is a group 0 element. Give the formula of a compound that is found in unpolluted air. So what compound would you typically find in unpolluted air? Sounds like a bit of a trick question. The answer here is carbon dioxide. We would expect to find 0.04% of air to be made up of carbon dioxide. That is not a pollutant. It's the fact that we're burning so many fossil fuels that's actually increasing the amount of CO2 in the atmosphere. Do make sure you provide a formula and do make sure that it's a compound. This apparatus in the diagram is used to find the percentage of oxygen in air. The large pile of copper powder is heated and the air in the syringe is passed several times from one gas syringe to the other. The large pile of copper powder turns black. The remaining gas is allowed to cool and its volume is measured. Explain why the large pile of copper turns black. Remember, it's due to the fact that the copper reacts with oxygen in the air to form copper oxide, which is black. Why is the gas allowed to cool before its volume is measured? Because remember, gas expands when it's heated and we want the accurate measurement here. The small pile of copper powder is then heated and the remaining gas is passed several times over the hot copper. The copper does not turn black. Suggests why the small pile of copper does not turn black. That must be because all the oxygen has reacted within the gas syringe. In another experiment, the total volume of air in the apparatus before heating is 150 centimeters cubed. At the end of the experiment, the volume of gas remaining is 125. Use this information to calculate the percentage of oxygen in this sample of air. So we do change in volume, which we can see is 25 centimeters cubed, divided by the original, which is 150, multiplied by 100, which is 16.7%. The reactivity series is a list of metals placed in order of their reactivity. Here's a copy of the reactivity series. So we start with the most reactive elements. That will be your group 1 elements. Remember, potassium, sodium, and lithium are all in group 1. After that, we have group 2 elements. Then we have some transition metals. Notice that the least reactive elements include your jewelry metals such as silver and gold, which makes sense. We find them uncombined in the Earth's crust, and obviously we need them to be unreactive because we hold them close to our skin. But if we have an unknown metal, how do we know where to place it in the reactivity series? I'm going to go through that right now. So when you determine the reactivity of an unknown metal, you want to start off quite low key, start with cold water, and then if it doesn't react with that, you're going to try with steam, so very hot water, and then we're going to try with acid. But start with cold water. From a safety point of view, it's essential that that reaction isn't too violent. So we place in cold water. If there's no reaction, we test with steam. And if there's still no reaction, we test with acids. Do be careful. Group 1 elements should never be tested with acid because you'd get a very violent, dangerous reaction. Let's look at some equations we might expect to see. So if you had potassium and you reacted it with cold water, then you would make potassium hydroxide and hydrogen. Let's write a balanced symbol equation. There's the formula of potassium, there's water, potassium hydroxide. I've shown you how to work out the formula previously. It's absolutely fine to write KOH there, and hydrogen is a diatomic element. It exists as 2 atoms, so that's why you need to write H2. Let's balance it. I'm going to eyeball this. We've got 2 hydrogens here, 3 over here, so I know that I definitely need a 2. This increases my number of oxygens to 2. I've only got 1 there, so I'm going to place a 2 here. So my hydrogens and oxygens are balanced. Just sort out the potassium right there. Let's look at another example. What about calcium and steam? Steam is water. This time you make calcium oxide and hydrogen. Let's write the balanced symbol equation. Calcium is in group 2, oxygen is in group 6, so those are the charges on the ions. That's the formula of calcium oxide. Just make sure it's balanced. Yes, this one is, so that's good. So I've done an example with cold water, I've done an example with steam. What about an example with acid? Let's take zinc and hydrochloric acid. You're going to make a salt, which is zinc chloride plus hydrogen. We've got Zn. The formula of hydrochloric acid is HCl. What about the formula of zinc chloride? Zinc is one of the transition elements, so you need to learn that it has a charge of Zn2+. Chlorine is in group 7, so it's Cl-. Therefore, we need ZnCl2 for our neutral formula, plus our H2. Now get it balanced. 2 chlorines on the right, 1 on the left. So we need a 2 there, and everything else is fine, so that is balanced. So just a little bit of practice there on writing word equations and balanced symbol equations. So in terms of determining the reactivity of our unknown metal, we know we can test it first of all with cold water, then with steam, then with acid, but you can also use displacement reactions in order to arrange metals in order of their reactivity. What you'll find here is that the less reactive element is pushed out of its compound by a more reactive element. So let's look at an example. I'm interested in magnesium and copper's relative reactivities. So I'm going to take magnesium, I'll react it with copper oxide. Now there is a reaction, so that magnesium will displace the copper to form magnesium oxide plus copper. Let's look at our equation. Mg plus, here are your 2 ions making up your copper oxide. This is why I said previously that it's so important that you can write the formula. You need to practice this lots if you're unfamiliar. What about the formula of magnesium oxide? Magnesium is in group 2, oxygen is in group 6, nice and straightforward, plus copper. So there's your balanced symbol equation. Because displacement has occurred, we can infer that magnesium is more reactive than copper. What about in this example where we've got zinc reacting with copper sulfate? Zinc is more reactive than copper, so again you'll get displacement to produce zinc sulfate plus copper. Be prepared to state any observations. You've gone from having zinc, which is a silver-coloured solid, it's a metal. Copper sulfate, remember, is that beautiful blue solution. So when they react together, you've no longer got your silver solid or your blue solution. So actually, you're going to see the solution turn colourless. And you might even see a pink solid form, which is your copper. So do be prepared to state what you would see. The reactions in metals with water and with dilute sulfuric acid can be used to determine the order of reactivity of the metals. The table shows the reactions of 4 metals with water and with dilute sulfuric acid. What is the order of reactivity of these metals? So let's have a look with water first of all, because it won't be such a strong reaction compared with the acid. So the one which reacts most quickly with water must be the most reactive. And as you'd expect, it's quite a dangerous reaction with sulfuric acid. Then we have a very slow reaction with water. So that must be our second most reactive. And now we're comparing the 2 with no reaction. We need to look at their reaction with sulfuric acid to put those 2 in order. It's going to be this one at position 3 and this one at 4. So what order did I say? I said Z, X, Y, W, which is B. State which metal could be copper. So we're looking for a very unreactive metal because copper sits below hydrogen in the reactivity series, which includes hydrogen. So we need no reaction with either acid or water, so it must be W. Which metal could be magnesium? We'd expect it to react with sulfuric acid and to show a slow reaction with water, so the answer here is X. A displacement reaction can also be used to decide the order of reactivity of 2 metals. State 2 observations made when an excess of magnesium powder is added to aqueous copper 2 sulfate. Let me just show you this equation. Because it's a displacement reaction, the more reactive magnesium replaces the copper. Just think about what's happening. you've got copper sulfate, which is blue. You no longer have copper sulfate, so you're going to have a colourless solution formed. We're going to lose our silver metal here, which is magnesium, and think about what colour copper is. We're going to gain a pink metal. So pink solid forms. Solution turns colourless. The rusting of iron topic. Now, rust very specifically refers to the element iron corroding. Other metals corrode, but really it's only iron that rusts. You need two things present in order for rusting to occur. You need both oxygen and water. If you're missing either of those things, then rusting will not take place. Things like salt do increase the rate of rusting, but they're not necessary for rusting to occur. So what is the overall reaction? Well, iron plus oxygen plus water produces hydrated iron 3 oxide. You can see rust really clearly. It looks like an orange flaky substance. How can we stop our objects from rusting? After all, a large number of objects like cars and bridges and buckets are made out of iron. Well, the first thing we can do is provide a barrier to the oxygen and the water in the form of grease, oil, or paint. When you think about a particular situation, think about the most practical way to prevent that iron from rusting. Something like a car and a bridge is quite large, so paint is a good cost-effective option here. However, if that paint layer gets damaged, the iron can immediately rust. More complicated ways of preventing rusting include galvanizing, which is when you coat the iron in a more reactive element like zinc. What happens is that the zinc reacts preferentially over the iron in a process known as sacrificial protection. If we go into slightly more detail, what happens is the zinc forms zinc ions, Zn2+, and releases electrons. Those electrons can flow to iron, therefore preventing the formation of any iron ions. Sometimes you'll see people attach zinc blocks to the hulls of ships. Again, that will help prevent that iron from rusting. And the great thing is, particularly in galvanizing, if the layer is damaged, then the iron won't rust because of the ability of the zinc to donate electrons. This question is about the rusting of iron. Water is needed for iron to rust. Name one other substance needed. I just mentioned that it's oxygen. Give the chemical name for rust. It's iron 3 oxide. The diagram shows two methods used to prevent iron from rusting. Method A will only work if the plastic coating is not damaged. Method B will work even when the zinc coating is damaged. Explain how method A prevents iron from rusting. Okay, we can see quite clearly that plastic is being used as a barrier method, preventing oxygen and water from reaching the iron. Give the name of method B. Because it's involving a coating of zinc, it must be galvanizing. Explain how method B prevents iron from rusting even when the zinc coating is damaged. The zinc is more reactive than iron and therefore reacts in preference to iron. Oxidation and reduction now. Oxidation refers to the gain of oxygen and the loss of electrons. Reduction refers to the gain of electrons and the loss of oxygen. Use oil rig to help you remember the definitions in terms of electrons. Oxidation is loss of electrons, reduction is gain of electrons. A redox reaction is a reaction where both reduction and oxidation occur at the same time. Be prepared to identify which species is undergoing reduction, so either losing oxygen or gaining electrons, and which species is undergoing oxidation, so gaining oxygen and losing electrons. An oxidizing agent is a substance which causes another species to be oxidized, i.e. that other species gains oxygen or loses electrons. A reducing agent, as the name suggests, causes another species to be reduced, so the other species will either gain electrons or lose oxygen. Right, let's look at this equation here to try and work out what's been oxidized, what's been reduced, what's acting as an oxidizing agent, and what is acting as a reducing agent. So we'll start with which species has been oxidized. So you must remember your definition of oxidation here. We want the one involving electrons because we've got charges, which means the electrons have been lost or gained, and after all, there's no oxygen. So remind yourself that if it's been oxidized, it must have lost electrons. So now scan through the 4 species here and work out what has lost electrons. If it's lost electrons, it's going to become positively charged. So the magnesium here has lost electrons to become Mg2+. So which species has been oxidized? It is magnesium because it's lost electrons. And you can even see the half equation and how that actually makes sense. Look, the Mg has indeed lost electrons to become Mg2+. Part B, which species has been reduced? So which species has gained electrons? So which species has gained electrons in order to become neutral? Well, you can see very clearly that it's the silver ion, because it's gained electron to become neutral silver atoms. And again, I can show you the half equation that proves that. There it is, gaining electrons to become silver atoms. So which species is acting as the oxidizing agent? So you need to ask yourself, which species has caused the other species to be oxidized? Well, we know the magnesium was oxidized, so which species must have caused that? It must be the Ag+. So Ag+ is the oxidizing agent because it causes Mg to be oxidized. That Mg has lost electrons. And then finally, which species is acting as the reducing agent? So which species causes the other species to be reduced? Remember, we identified the Ag+ as being reduced, so it must be the magnesium that's responsible for that. And overall, we can say that a redox reaction has occurred because you can see that both oxidation and reduction have occurred, and be prepared to point out what has been oxidized and what has been reduced. A mixture of zinc powder and copper oxide is heated. The chemical equation for the reaction that takes place is: state how the reaction shows that zinc is more reactive than copper. You can see that zinc has displaced the copper. Explain which substance is the oxidizing agent. So which substance is causing another substance to be oxidized? Let's work out which substance is being oxidized. It's the zinc, because after all it gains oxygen. So what must the oxidizing agent be? It must be the CuO. And if you're not sure, please just write the formulae of the substance in your answer to avoid any errors being introduced. So you write copper oxide acts as the oxidizing agent because it causes zinc to be oxidized, i.e. gain oxygen. Seawater contains bromide ions. Bromine can be obtained by bubbling chlorine through a sample of seawater. The Ionic equation for the reaction is: explain which species acts as an oxidizing agent in this reaction. So because we've got charges in this equation, it's going to be oxidation and reduction definitions involving electrons as opposed to the oxygen definitions. Also notice there's no oxygen in there. So which species is causing another substance to be oxidized, i.e. lose electrons? We'll have a look. The Br- is losing electrons to become the neutral Br2, and it is the Cl2 which is responsible for that. So Cl2 acts as, take your time here, an oxidizing agent because it causes the Br- to be oxidized, i.e. to lose electrons. Use the formulae in the question to stop any issues with accidentally saying bromine which would be this when you actually mean bromide. Acid bases and salt preparations. First of all, what is a salt? It's an ionic compound formed by the neutralization of an acid by a base. Remember that a base donates hydroxide ions, and a soluble base is known as an alkali. Salts are produced in neutralization reactions. The overall ionic equation for this is H plus ions plus OH minus ions produces water. So you've got an acid and an alkali reacting to produce your water. The acid, remember, donates the H plus ions. The base or alkali donates hydroxide ions. All acids contain hydrogen, so you'll notice the formula for hydrochloric acid is HCl, nitric acid HNO3, sulfuric acid H2SO4. All acids donate H plus ions, which are also known as protons. Now, the type of salt formed totally depends on the acid used. So if nitric acid is used, you'll produce a nitrate salt. Sulfuric acid is used, you'll produce a sulfate salt. If you use hydrochloric acid, you'll produce a salt containing chloride. They're very interested in asking about the salt solubility rules, which is super annoying because it basically means you just need to learn off by heart which salts are soluble and which salts are insoluble. It does take a little bit of practice. So let's go through some rules. All nitrates, so all salts which contain nitrate, are soluble. All salts which contain potassium, sodium or ammonium ions are soluble. All sulfates are soluble. The exceptions here are lead sulfate, barium sulfate and calcium sulfate. All chlorides are soluble, the exceptions being lead chloride and silver chloride. Now let's switch it to say that all carbonates are insoluble. The exceptions here are what we've previously mentioned. Ammonium, potassium and sodium carbonates are soluble. All hydroxides are insoluble. Again, the exceptions here are ammonium, sodium and potassium hydroxide. So see if you can practice this right now. I'm going to say some salt names and you need to decide if they're soluble or insoluble. So just pause the video. First of all, lead nitrate is soluble because it contains nitrate. What about ammonium carbonate? That's soluble because it contains ammonium. What about calcium sulfate? That is insoluble. What about silver chloride? That is insoluble. How about potassium hydroxide? That is soluble. So just practice writing out some salts and determining whether they are soluble or insoluble. Let's look at our various neutralization equations. I'm going to give you a summary and then we'll look through some specific examples on the iPad. So starting with, if you have a metal reacting with an acid, you're going to produce a salt plus hydrogen. If you have a metal hydroxide reacting with an acid, you'll produce a salt plus water. A metal oxide plus an acid produces a salt plus water. And then lastly, a metal carbonate plus an acid produces salt plus water plus carbon dioxide. In our first example, I'm going to take magnesium and hydrochloric acid. Just remember for me that if you have hydrochloric acid, you'll produce a salt containing chloride. If you've got nitric acid, you'll produce a salt containing nitrate. If you've got sulfuric acid, you'll produce a salt containing sulfate. So magnesium plus hydrochloric acid will produce the salt magnesium chloride plus hydrogen. Let's convert that into a balanced symbol equation. So start with your magnesium, use your periodic table to check its symbol. It's Mg. Learn the formula of hydrochloric acid, it's HCl. What's the formula of magnesium chloride? Well, magnesium is in group 2, it's a metal, so it has a positive charge, it's 2+. Chlorine is in group 7, so it's going to have a 1- charge. Watch a previous part of my video if you're not sure where I'm getting these charges from. What about the formula of magnesium chloride? Well, they're not balanced. You can see we need an extra chloride ion, so we show that by writing MgCl2. Let's get this out of the way to keep it nice and tidy. And then the hydrogen. Hydrogen, remember, is a diatomic gas. It requires 2 atoms, so it's H2. Check the balancing. I can see straight away that I need 2 over here to accommodate the extra chlorine needed. Just double check 2 hydrogens, 2 hydrogens, 2 chlorines, 1 magnesium. That's done. Let's take sodium hydroxide now and sulfuric acid. So the name of the salt in this case will be sodium sulfate. And then because we've got a metal hydroxide, our byproduct is water. Let's get that all converted to a balanced symbol equation. So sodium is in group 1, so it has a 1+ charge. The hydroxide ion, remember you need to learn that off by heart, it's OH-. These charges balance, which is nice because it means the formula of sodium hydroxide is just NaOH. Sulfuric acid, learn its formula, it's H2SO4. What's the formula of sodium sulfate? Na plus again, the sulfate ion needs learning off by heart. It's SO42-. We have issues with charges there, meaning that we need an extra sodium ion. So we show that by including a 2. There's the formula of sodium sulfate. Water is nice and straightforward. It's H2O. Double check the balancing. I can see I need an extra sodium over here, so I'm going to put 2. Just double check. I think I don't have enough hydrogens on the right hand side. Sure enough, I've got 2 here and 2 is 4 on the left hand side. Only 2 on the right hand side, so I'm going to pop a 2 there. Double check now. Oxygens, 6 on the left hand side, 6 on the right hand side. That is balanced. Now we're going to take a metal oxide example. So magnesium oxide plus hydrochloric acid. That's going to produce the salt magnesium chloride and then water as our byproduct. Let's convert that into a balanced symbol equation. Magnesium is in group 2, so it's 2+. Oxygen is in group 6, so it's O2-. They're happily balanced, so it's just MgO, the formula of magnesium oxide. Hydrochloric acid is just HCl. Magnesium chloride, there's the Mg2+ again. Chlorine is in group 7, so it's 1-. They're not balanced, so we need an extra chloride ion. We show that by writing MgCl2 plus H2O. Let's get it balanced. I'm going to add a 2 here, and then everything else seems to be balanced. Finally, I want to take a metal carbonate example. I'm going to take potassium carbonate and react it with hydrochloric acid. We're going to produce a salt, which is potassium chloride plus water, and then due to that carbonate, we're going to have another byproduct of carbon dioxide. Let's convert that. Potassium's in group 1, so it's 1+ charge. The carbonate ion, you need to learn off by heart, it's CO3 2-. Double check to see if they're balanced. They're not, so we need an extra K+ ion. We show that by writing a 2 there. So the formula of potassium carbonate is K2CO3. Hydrochloric acid is HCl. Potassium chloride's formula, you've got the potassium ion again, the chloride ion, they're balanced, so it's just KCl plus water plus carbon dioxide. Let's get it all balanced now. We have 2 potassiums here, only 1 there, so I'm going to put a 2 here. That means that we now have 2 chlorines, and we've only got 1 here, so I'm going to pop a 2 there. And then just double check, have you got enough carbon, hydrogens and oxygens? Yes, I do, so that's done. Let's now look more experimentally as to how we actually produce salts. In this required practical, we're being asked to make a soluble salt. So that's a salt which dissolves in water. And in terms of the reactants you'll need both an acid and an insoluble metal oxide or metal carbonate. In the example I'm going to show you, we're making soluble copper sulfate. Think about the acid we'll need. That will be dictated by the sulfates, so we'll use sulfuric acid. And my insoluble reactant will be my copper oxide. Just so you know, if you're asked to make a salt which contains a nitrate, you'll need nitric acid. If you need to make a chloride, you'll need hydrochloric acid. And as we know in this example, to make a sulfate, we'll be using sulfuric acid. So always bear in mind the appropriate reactant. But what about our method for making this salt? You'll get a mark for mentioning the correct reactants. Make sure you include any suitable apparatus. So I'm going to say, for this example, add sulfuric acid and copper oxide to a beaker and stir. We want our insoluble reactant to be in excess, so continue adding copper oxide until it's in excess, and you'll see no more fizzing occurring, no more effervescence. We need to remove any unreacted copper oxide, so we're going to filter the mixture using a funnel and filter paper to remove excess copper oxide. Now our next step is to evaporate some of the water, so we're going to heat the mixture using a Bunsen burner and evaporating basin until the crystallization point has been reached. And then our last step is to allow our salts to dry. So leave to dry, and do specify how you're doing this on filter paper. So zooming out, here's my detailed method as to how I'm making copper 2 sulfate from sulfuric acid and insoluble copper oxide. I just want to show you the apparatus. So we've already reacted our copper oxide together with our sulfuric acid. We've made sure the copper oxide is in excess, so then we're using the filter paper and the funnel to remove any unreacted copper oxide, leaving us with a saturated copper 2 sulfate solution, which we've placed in an evaporating basin. This gets put on top of a wire gauze on top of a tripod, which has a Bunsen burner underneath. We're going to use that Bunsen burner to heat our solution in order to evaporate some of the water to reach that crystallization point. And then our last step is to leave those crystals to dry. A salt can be made by reacting an acid with an insoluble base. A student has a sample of copper oxide. The student uses this method: pour 50 centimeters cubed of dilute sulfuric acid into a beaker, warm using a Bunsen burner, add a small amount of copper oxide and stir, add further amounts of copper oxide until it's in excess, filter, obtain crystals. State why the acid is warmed in stage 2 to increase the rate of reaction. State how the student would know that the copper 2 oxide is in excess in stage 4. Copper 2 oxide solid settles at the bottom of the beaker. You're not going to see it dissolving any further. Why is the mixture filtered in stage 5? To remove any unreacted copper 2 oxide. State the colour of the filtrate obtained in stage 5. Think about what the salt is you're going to be making. You've got copper oxide reacting with sulfuric acid, so you're going to be making copper sulfate. Copper sulfate, remember, is blue. Describe how the student could obtain a pure dry sample of hydrated copper 2 sulfate crystals from the filtrate in stage 6. So our first step is to heat the filtrate. Why? To evaporate some of the water. You want to allow your solution to cool. Then you want to filter to remove the crystals. Leave to dry on filter paper. Let's look at ion tests and tests for gases. So I'll start with your typical lab test for gases. I'm keeping this very concise. So if they ask you how to test for hydrogen, you're going to use a lit splint, and if hydrogen is present, it will burn with a squeaky pop. What about our test for oxygen? Rather than a lit splint, you want a glowing splint, and if oxygen is present, it's going to relight. Our test for carbon dioxide, we're going to bubble through lime water, and if carbon dioxide is present, you'll see that lime water turn cloudy, and that's due to the presence of insoluble calcium carbonate. Our test for chlorine, we're going to use damp blue litmus paper, which will be turning white or is bleached, both are fine. The fifth test is for ammonia. Ammonia turns damp red litmus paper blue. What about flame tests now? We use flame tests to test for positive metal ions. So in terms of the method, you want to dip a platinum or nichrome wire in your sample that you're testing. Then you want to hold that wire in a roaring blue flame of a Bunsen burner. It needs to be the hot flame, not the luminous orange, because the luminous orange will mask the color change. And then you need to observe the color change. And you must learn these colors for me. They're listed in the specification. If you have lithium ions, you'll see a crimson red flame. If you have sodium, you'll have a yellow flame. Potassium is a nice purple lilac flame. Calcium is orange red, a brick red shade, and copper will be a green flame. So that's how you carry out a flame test. In addition to a flame test, you can use sodium hydroxide to identify some metals. So once we add sodium hydroxide, you're going to get various precipitates. If you were to add sodium hydroxide to copper 2, you'll get a blue precipitate. If you have iron 2, you'll get a green precipitate. And then lastly, if you have iron 3, you'll have iron 3 hydroxide, which is a brown precipitate. They could ask you to write an ionic equation. I'm just going to do an example here for iron 3. There's your Fe3 plus ion reacting with the hydroxide ion to form FeOH3, which is a solid because it's a precipitate. Do make sure that everything's balanced. You must practice writing your formulae. Remember, that's produced from combining Fe3 plus and 3 hydroxide ions. If you're asked to test for the ammonium ion, which is NH4 plus, what you're trying to do is get your sample to release ammonia. So you add sodium hydroxide, you won't get a precipitate. Instead, you'll get a choking gas released, which is likely to be ammonia. And then you just need to check its identity. That gas should turn damp red litmus paper blue. And if these things happen after you've added sodium hydroxide, then you know the original sample contained the ammonium ion. Now we're moving on to our negative ions. So the first negative ion I want to look at is testing for carbonates, which is CO3 2-, that's the charge of the carbonate ion. You want to add an acid, and what you'll see happen is fizzing, which indicates a gas has been released. What gas is it? It's going to make sense that it's carbon dioxide. And to just prove its identity, we want to bubble through lime water, and obviously we'll expect that lime water to turn cloudy. The second negative ion we want to test for, the second anion, are the halides, so group 7, specifically the chloride ions, the bromide ions, and the iodide ions. In terms of our method, you need to add nitric acid to remove any carbonate ions which might interfere with the result because they're insoluble. And then we add silver nitrate. And then I'm going to write some ionic equations to show what's happening. So this is going to be silver chloride, which is a white precipitate. You must learn that. So there's our chloride. What about if we have bromide? We'll have silver bromide, which is a cream precipitate. And then lastly, if we have iodide ions, silver iodide is a yellow precipitate. And then the last test I promise is the test for sulfates, SO42-. Your method this time is to add hydrochloric acid, add barium chloride, and a positive result for sulfates is a white precipitate, which is actually barium sulfate. To show you that ionic equation now. And remember, my revision guide has all of them. Let's discuss water a little bit now. If they ask you about a chemical test for water, you want to say that white anhydrous means that there's no water present. Copper sulfate turns blue in the presence of water. The physical test is all to do with checking melting and boiling points. So you want to check the boiling point. If your substance boils at 100 degrees, you know you have water. How do you check if you've got pure water? Check the boiling point again, and you need one fixed boiling point of 100 degrees. If it's boiling over a range of temperatures, then you don't have pure water. The student does 2 tests on a solution made from a white solid, a flame test, and adds acidified silver nitrate solution. So I know I'm testing for the halide ions, which is group 7. The table shows his results. We've got a flame test where the flame turns red. That means automatically I've learned all my colours. It's a lithium ion. Add acidified silver nitrate solution. We've got a cream precipitate. Remember those dairy colours? It goes chloride, bromide, iodide, white, cream, yellow. So it's going to be the bromide ion for cream. Give the formula of the ion that produces the red flame. It's lithium. Name the cream precipitate. So we know that the cream precipitate is produced from the bromide ions. If I write you the ionic equation, we know it's silver ions reacting with bromide to form the cream precipitate of silver bromide. So the answer is silver bromide. Identify the white solid. So what did we have to begin with? Well, we must have had lithium bromide. The student uses a clean metal wire in the flame test. State why the wire should be clean when used in a flame test, because you don't want any impurities which would mask the colour of the flame. The table lists properties of some metals. Add ticks to the table to show the 2 properties needed in a metal wire used in the flame test. Right, I told you it needs to be unreactive, inert, and have a high melting point so it doesn't melt in the blue flame of the Bunsen. Now we'll look at all the reactions to do with temperature changes, and that involves endothermic and exothermic reactions. Remember, endothermic reactions take in heat energy from the surroundings. And so as a result, the surroundings get cooler. So you'll see the temperature decrease when you measure that with a thermometer in an endothermic reaction. Exothermic reactions release heat energy to the surroundings. So the surroundings get hotter. And so with our thermometer, we'll find that the temperature has increased with an exothermic reaction. It's very important that you're aware of that. Let's look at these energy level diagrams. So with our exothermic reaction, remember that delta H, our energy change, is negative. And what that means is that our products have less energy compared with our reactants. So do make sure that these reactant lines are higher compared with the products. The difference between those two lines is your energy change. With an endothermic reaction, delta H is positive, and as a result, your products have more energy than your reactants. So the product line is higher than that of the reactants. Again, you can find the energy change. A couple of extra key definitions. So what is a catalyst? It's a substance which speeds up the rate of reaction without being used up. Activation energy. This is the minimum amount of energy required for reaction to take place or occur. If they ask how a catalyst actually works, you need to combine both of these by saying catalysts work by offering an alternative reaction pathway with lower activation energy. So if we look at our exothermic and endothermic reaction profiles again, let's actually have a look at labeling a catalyst. So if they ask you to label a catalyst, what you want to do on the exothermic reaction pathway is show a small peak like that, bring it down to the products, and you want to label this here as your activation energy. It's very specifically that part of the profile. If you're asked to show how a catalyst affects your exothermic reaction, you just need to show a lower peak. And as you can see, the catalyst has indeed lowered the activation energy. Let's now do it on the endothermic profile, just to check you know what's going on here. So this is your activation energy again. And if they ask you to show how a catalyst affects that, we're going to lower that peak again. So we have lowered the activation energy by adding a catalyst. In terms of examples of endothermic reactions, we've got cold packs used for sports injuries. Exothermic examples include hand warmers and self-heating cans. Now, the way in which we can investigate the endothermic and exothermic reactions include the following. So we could add a salt to water, such as sodium chloride, the salt, we add it to water. Neutralization reactions, an acid reacting with an alkali. An exothermic reaction, the temperature will increase. Displacement reactions, so when a more reactive metal displaces a less reactive metal. And combustion reactions, which is all to do with burning fuels like the alkane methane. This is a really typical setup. So here we're adding sodium chloride to water. We've got a polystyrene cup which is acting as a good insulator, and that's going to prevent heat loss to the surroundings. We might choose to add a lid again to further reduce heat loss. When we add the two substances together, we'll want to stir to ensure that they're fully mixed so that a maximum temperature can occur. A couple of calculations now. I want to show you this one. Q equals mc delta T. Q stands for energy. M stands for the mass of solution. That's important. It's the mass of solution, not the mass of solid. So if you're adding two solutions, it's both of their masses added together. C is the specific heat capacity. That's a very specific number. They usually give it to you. Delta T means change in temperature. So bear in mind what each of these things mean. You could also be asked to find delta H. Now delta H is the enthalpy change, and it's given by Q over N. So you'll often find these questions combined. In the first part of the question, you'll be asked to find Q, and then later on you sub that into this equation in order to find the enthalpy change. Now N stands for the number of moles. We're very used to finding the number of moles. Most often you're just going to use number of moles is mass over MR. So a little bit of a link with the moles topic, but always remember that for me. One thing I want to say is be careful with units here. Delta H is often given in kJ per mole, which means that if you have found out your energy change earlier on in the question in joules, you'll need to divide by 1,000 to get it into kilojoules. I'll show you some examples so it doesn't seem as complicated. And the last thing you need to remember is to include a sign. You want to either include a plus sign in front of your final answer or a negative sign. Remember, plus means that you have an endothermic reaction. The minus sign means you have an exothermic reaction. And you'll know that from information given in the question, because if the temperature has increased, it's an exothermic reaction. So if the thermometer reading has increased, you need to put a minus sign at the beginning of your answer. If the thermometer reading has decreased, you need to put a plus. So let's really put into practice what I was just saying. So here's a very typical example. In an experiment, 0.6 grams of propane was completely burned in air. The heat evolved raised the temperature of 100 grams of water by 64.9 degrees Celsius. The specific heat capacity of water is 4.18. Calculate the heat energy given off in joules. So the equation we need is Q equals mc delta T. We're being asked to find the heat energy, so I'm after Q. What is the mass? Be careful here. Remember I said it's the mass of solution, so you must ignore the 0.6 grams and use 100. The specific heat capacity of water, they've told us, is 4.18. What is the temperature change? We can see that the temperature was increased by 64.9. Put that into your calculator and you'll get a value for Q of 27,128 joules. Calculate how many moles of propane were burnt. So we do number of moles is mass over mR. The mass they told us was 0.6 grams. What is the mR of propane? Use its molecular formula there, it's C3H8. So carbon, use your periodic table, has a mass of 12. Hydrogen has a mass of 1. Put that into your calculator and you'll find a number of moles, which looks like this. And then in part C, it's asking us to calculate the enthalpy change of the reaction in kJ per mole. So we're after delta H, which remember we said is Q over N. Just be a little bit careful with your units. It wants your answer in kJ, whereas our previous part of our question just had it in joules, so you need to divide that number by 1,000 to get 27.128. We just found the number of moles, so our answer here is 1989 kJ per mole. Do not lose a mark by not including a sign. What is the sign? Well, you have to look at what happened with the temperature change and work out if it's an exothermic or endothermic reaction. So we check the wording of the question. It says that the heat evolved raised the temperature by 64.9 degrees. Therefore, I know that it's an exothermic reaction, and I show that by including a negative sign. Aluminium reacts with iron 3 oxide. The reaction is exothermic. The equation for the reaction is, state how the equation shows that iron 3 oxide is reduced. So in this particular question, we need the definition of reduction, which means loss of oxygen. So you can see that the iron oxide has obviously lost oxygen because it's gone from iron oxide to iron. Draw an energy level diagram for the reaction between aluminium and iron 3 oxide. So here are our reactants. These are our products, and we've been told that the reaction is exothermic, which means that our products need to sit at a lower energy level compared with our reactants. So let's obey that here. There's my reactants. And here are my products at a lower energy. A student uses this apparatus to investigate the temperature change that occurs when ammonium nitrate is dissolved in water. She uses this method. Put 100 centimeters cubed of water into the polystyrene cup, measure the initial temperature. Add 8 grams of ammonium nitrate, stir, record the lowest temperature reached. Because the temperature's gone down, I know it must be an endothermic reaction. The table shows her results. Use the results of the experiment to explain what type of reaction is taking place when ammonium nitrate is added. Oops, I keep doing this, answering the question before I see it. So it's an endothermic reaction because the temperature has decreased. And let's define what an endothermic reaction is. Heat energy has been taken in from the surroundings. Show that the heat energy change is around 2,400 joules. So Q equals mc delta T. We're after Q. What is the mass? It's the mass of water, which is 100 centimeters cubed, converted into grams, so that's just 100 grams. We're told the specific heat capacity is 4.18. What is the temperature change? It's 5.8. So put that into your calculator, you'll get a value of 2,420, which is approximately 2,400. So I know I've definitely got those 3 marks. Use your answer to part B to calculate the enthalpy change in kilojoules per mole. Here's your MR, include a sign. So delta H equals Q over N. Just be careful with your units. It needs to be in kilojoules, so that becomes 2.42. What is our number of moles? Well, it's the mass of ammonium nitrate added, which was 8 grams, divided by the MR, which they've given us, which was 80. So we've got 0.1 moles. Do 2.42 divided by 0.1 to get 24.2. And then they want a sign in your answer. Remember, we said it's an endothermic reaction, which is shown by a plus sign. And that's how I guarantee 4 marks. The rates of reaction topic is all about how quickly reactions take place and how you can alter the conditions to increase how fast that reaction is occurring. So the usual thing you'll see is a solid reactant, such as calcium carbonate, being added to an acid. A gas will be produced, and we can measure the volume of gas produced over a set time period using a gas syringe. Obviously, the more gas that's collected in a set time period, the faster the rate of reaction. What factors affect the rate of reaction? Well, you could be asked about temperature, concentration of solution, and surface area. Remember, you can also add a catalyst. A catalyst speeds up the rate of reaction without being used up by offering an alternative reaction pathway with lower activation energy. So we'll go through temperature, surface area, and concentration right now. So why does increasing the temperature increase the rate of reaction? Well, it's because your reactant particles have more kinetic energy. There's an increase in the frequency of successful collisions per unit time. And this kind of wording I'm using now is the sort of thing you need to include in your exam answer. What about concentration? Well, if you increase the concentration, you increase the number of reactant particles present in the same volume. It is key that the volume remains the same. And as a result, you get an increased frequency of collisions per unit time. So you can see the wording is very similar for both. What about the effect of surface area? Now, powdering a solid reactant, like calcium carbonate limestone, will always increase the rate of reaction compared with if you keep it in large chips. And that's because if you powder something, you increase the surface area, meaning that there's an increased frequency of collisions per unit time. Let's have a look at some key graphs. So as you can see, we're comparing temperature here. When you've got a higher temperature, you'll expect a high rate of reaction, and that's shown by the red line here, where we see a steeper gradient. Notice, because we haven't altered the concentration or the mass of reactants, you will actually end up with the same mass of product produced. So both graph lines plateau at the same place. If we compare concentration from a graph point of view, when you have twice the concentration, you produce twice the mass of product. So despite the fact that the gradients have remained very similar, you'll produce more when you've doubled the concentration of your solution. The last graph I want to look at concerns surface area. As I said, if you powder your solid reactant, you're going to end up with a steeper gradient, but because you've kept the masses the same, you'll actually produce the same mass of product. It's important that you can draw these graph lines really accurately, make sure you actually understand what's going on. So we can measure the rate of reaction by either looking at the quantity of reactants used or the quantity of products formed, and dividing that by the time taken. And if we actually look at a particular experiment, here we have marble chips, which are calcium carbonate, reacting with hydrochloric acid in a conical flask. So obviously what happens if we look at the summary equation is that the calcium carbonate reacts with the hydrochloric acid to form calcium chloride plus carbon dioxide plus water. And it's specifically the product of carbon dioxide that we're monitoring here. Because carbon dioxide is a gas, it will be released out of the top of the conical flask. We use the cotton wool to stop the acid spraying out, but we can't use a bung because that would prevent the carbon dioxide leaving. And because CO2 has a heavy MR, its MR is 44, you can calculate that using the periodic table, you'll see the reading on the balance decrease over time. Another setup could be using a conical flask again, but this time attached to a delivery tube and a gas syringe, and this time we're measuring the volume of gas released in a particular time frame. I just wanted to use this past paper question to highlight one of the other experiments they could ask you about because it's slightly more complicated. It involves the reaction of hydrochloric acid with sodium thiosulfate according to this equation, which they will never expect you to rewrite, but I do want you to actually understand what's going on here. So the way the experiment works is your sodium thiosulfate mixes with your hydrochloric acid. It produces a solid, a precipitate of sulfur, which we can see right here in the equation. So the solution turns cloudy due to that precipitate. So the person watching the experiment, what they find is after a certain time frame, the cross on a piece of paper is obscured, and they'll record the time it's taken for that cross to be obscured after the reactants have been mixed. Clearly, the faster the time the cross has been obscured, the faster the rate of reaction. So just be aware that this is a different way in which we can monitor rate of reaction. So when they say state the name of the precipitate that forms, just check the state symbols on the products. It must be sulfur due to that solid state symbol. A student uses this apparatus to investigate the rate of reaction between magnesium and an excess of hydrochloric acid. She uses this method, use a beaker to pour 50 centimeters cubed of HCl of concentration this, add a piece of magnesium ribbon, put the bung on the neck of the flask and measure the total volume of gas collected every 10 seconds until the reaction stops. Plot the student's results on the grid, draw a line of best fit. Let's have a look at the data. Let's draw a curved line of best fit. The student repeats the experiment using the following mass of magnesium and 50 centimeters cubed of 2 molar. Draw on the grid in part A the curve you'd expect in this experiment. Label the curve Y. So let's make a comparison. So if we look at the masses, we've got half the mass of magnesium this time. What about the HCl? That's remained the same. So as a result, you'd expect half the volume of hydrogen to be released. The student repeats the experiment again using 0.086 grams of magnesium. So this is the same mass as the initial experiment, 50 centimeters cubed of 2 molar hydrochloric acid, so that's the same. But we've got a higher temperature, which means we're going to have a faster rate of reaction. Draw on the grid in part A the curve you'd expect. Label this Z. So we're just expecting the same volume released of hydrogen, but in a quicker time frame, so we need a steeper gradient. The expected volume of gas produced in the first experiment is 86 centimeters cubed. Suggests why the volume collected is less than the expected volume. Some gas escapes before the bung has been replaced. The student uses a graduated beaker to measure the volume of dilute HCl. Explain why it is not necessary to use a measuring cylinder in this experiment. They told us, remember, that the acid is in excess and therefore a precise measurement of its volume is not needed. The ionic equation for the reaction between magnesium and HCl is: use the information in this equation and particle collision theory to explain why the rate of reaction decreases during each of the experiments. It's up to you if you want to use the ionic equation. You can just go with your usual particle collision theory and state that the concentration of acid decreases, meaning that there are fewer successful collisions per unit time, or you could say that the concentration of H plus ions, which remember is the acid, decreases. It's up to you. Chemical equilibria and reversible reactions. So just to give you a little bit of a background, in chemical reactions, we are always trying to make as much product as possible, and we call that the yield of product. However, some reactions are really annoying, and what can actually happen is the product can break back down to form the original reactants, which quite frankly is a huge waste of time, energy and money, etc. So in this topic, we're going to be looking at how we can alter reaction conditions, namely temperature and pressure, as well as the addition of a catalyst, in order to produce as much of that product yield as possible. We also need to be aware of the factors which affect how quickly the reaction occurs. Remember, that's when we talk about collision theory and rates of reaction. So in this topic, we're going to be including a previous topic, rates of reaction, as well as introducing new concepts to do with yield. So the first thing to be aware of is the reversible arrow. It's a double-ended arrow showing that the forward reaction occurs as well as the reverse reaction. The organic chemistry topic is a huge topic. Organic chemistry is all to do with the element carbon. So most of the organic substances you'll meet will be hydrocarbons. A hydrocarbon is simply a compound containing carbon and hydrogen only. You must include only in your answer to get the second mark. Let's quickly just talk about a few formulas. It's important that you can distinguish between these. So a molecular formula tells you the actual number of atoms of each element present in a compound. So if I took ethene, that would be C2H4. The empirical formula is the simplest ratio of atoms of each element present in a compound. So what is the empirical formula of ethene? Well, we need to simplify C2H4 to its simplest ratio to become CH2. CH2 is the empirical formula of ethene. The structural formula shows how the atoms in a compound are joined together, and a displayed formula shows the bonds between the atoms. Let's use this example here to really spell out the difference between the different types of formula. So we're going to use propene, which is the second alkene. Its molecular formula, so the actual number of atoms of each element present in the compound, is C3H6. We have exactly 3 carbons and 6 hydrogens. The empirical formula, however, as it's the simplest ratio of atoms of each element, means that we need to simplify the C3H6, as I've done here in my guide, and it's become CH2. The general formula you'll need to learn off by heart for the alkanes, the alkenes, the alcohols, it's just CnH2n, where n refers to the number of carbon atoms. The structural formula is really a condensed version of the displayed formula. It shows you the functional group of a particular homologous series, but without having to draw out all the bonds, so we can see the location of the double bond in propene according to this structural formula. And then lastly, the displayed formula will show all the bonds present between the atoms. Now, there are lots of different organic compounds, and we like to divide them into families based on their chemical properties. The simplest hydrocarbons are the alkanes, and they obey the general formula CnH2n plus 2. A functional group is a set of atoms which is responsible for the chemical properties found within a compound. A homologous series refers to a family of compounds. Members of the same homologous series have the same chemical properties, the same general formula. They show a trend in physical properties, so that could be increasing boiling point, for example. Examples of a homologous series include the alkanes, alkenes, alcohols and carboxylic acids. Let's start by looking at the simplest homologous series, the alkanes, which obey the general formula of CnH2n plus 2. Remember, the N is the number of carbon atoms. So if N equals 1, what is the molecular formula of the first alkane? It's going to be C1H. 2 times 1 is 2, plus 2 is 4. So the first alkane has the molecular formula of CH4, because we don't need that 1 there. We'll streamline it. What is its name? Well, use the mnemonic monkeys eat peanut butter to help you remember that the first alkane is methane, the second one is ethane, the third one is propane, and the fourth one is butane. So it's a really neat mnemonic to help you remember the starting bits of each of the alkanes' names. So the first one we've just said is methane. Let's draw its displayed formula. One thing I want you to be aware of is the number of bonds that each element forms. You have to learn this because it will help you draw it nice and accurately. Carbon must always form 4 bonds. Hydrogen forms 1 bond. Oxygen forms 2 bonds. So if we obey that here, when we draw the displayed formula of methane, there's our carbon. We know we need 4 hydrogens around it, and we're going to arrange it like this because we're obeying carbon needing 4 bonds and hydrogen requiring 1 bond. Let's move on and increase our number of carbon atoms to 2. What is our molecular formula this time? So N equals 2. 2 times 2 is 4, plus 2 is 6. So the molecular formula is C2H6. What is its name? Well, it's the second alkane, which means it's ethane. And then we can draw it with its 2 carbons, fill up with hydrogens, making sure that all the bonds add up. Each carbon atom has 4 bonds, each hydrogen atom has 1 bond. Moving up again, the number of carbon atoms is 3. C3H8 is the molecular formula. The third alkane I've listed is propane. Draw it nice and carefully for me. There's the 3 carbons, complete with hydrogens to obey the molecular formula C3H8. Let's take 4 carbons now. So according to CnH2n plus 2, the molecular formula must be C4H10. Monkeys eat peanut butter, so we have butane. And then just draw that displayed formula nice and carefully. A few extra things to point out now. First of all, the alkanes are saturated. They often like to ask you why. It's because all their carbon bonds are single. And you can see that from the displayed formula. Look, every single carbon bond is single. Let's look at an alkane reaction with the halogens. The first thing to be aware of is that they react in what's known as a substitution reaction. That is the type of reaction that takes place. If we look at an example, I'm going to take this alkane. Practice, it's made up of 1 carbon. It's the first one, so that's monkeys, so methane. I'm going to react it with bromine, which remember is a diatomic molecule, as all the halogens are. Because it's a substitution reaction, think about what that word actually means. We're substituting one of the hydrogens for bromine. Doesn't matter which one. And then make sure that you just account for that hydrogen and the remaining bromine by showing that as your byproduct. You do need a special reaction condition to make this reaction occur, and that is the presence of UV light. What is the name of everything? We said that's methane. We said that this is bromine. This is bromo, because of the bromine, methane. And lastly, we've got hydrogen bromide. Now let's consider alkenes. Alkenes obey the general formula of CnH2n. We say that they are unsaturated, and if they ask you what that means, it's because they contain a C double bond C as a bare minimum. We're going to use the mnemonic monkeys eat peanut butter again to help us name them. Don't make life difficult for yourself. Use all these little tricks to help you. Now, methane does not exist, and the reason for that is because you need a minimum of 2 carbons to have an alkene. Then you have ethene, propene, and then butene. Let's input this into my table. So we know that with 1 carbon it's not applicable because we need a minimum of 2 carbons to reach our C double bond C. With 2 carbons, we're obeying the general formula CnH2n, so we know that the molecular formula will be C2H4. Monkeys eat, it's the second one, so it's ethene. Then draw it carefully. We need that double bond between the carbon atoms. And as I've said previously, make sure you count your bonds. Each carbon atom should form 4 bonds. Each hydrogen atom should form 1 bond, and that will ensure that you draw your displayed formula accurately. What about for 3 carbons now? CnH2n, so that means the molecular formula is C3H6. Monkeys eat peanut, so it's propene. Draw it carefully. There's the double bond. There's the 3rd carbon. Fill up with hydrogens. Each carbon has 4 bonds. Each hydrogen has 1 bond. 4 carbons now, C4H8. This is butene. 1, 2, 3, 4 carbons, fill up with hydrogens. And that's your displayed formula of butene. Just be a little bit careful here. Technically speaking, this is actually butanene, and that's because the carbon-carbon double bond appears on the first carbon. That's what the 1 indicates. However, you could also arrange the atoms like this, with the carbon-carbon double bond on the 2nd carbon. So I just want to show you the difference in these. So technically speaking, this is butene because it contains the double bond on the 2nd carbon. They're both still obeying the molecular formula of C4H8. Count them if you don't believe me, and you'll see that they do. So actually what we have here is what's known as isomers. So I'm going to write the definition. It's compounds with, look, what do we have here? The same molecular formula, but different displayed formula. As seen very clearly here from butanene and butyrene. Let's check their reactions. Let's look at alkenes reacting with bromine. This is known as an addition reaction. If we take an example like ethene reacting with bromine, because it's an addition reaction, think about what that actually means. You're going to add the bromine to the ethene, and the way you can do that is by breaking the double bond, because it actually gives you the space to add those atoms. So that means you won't end up with any byproduct, because look, you've accounted for all your atoms. There's actually a strong colour change here, which is it turns from orange due to the presence of the bromine to colourless because the bromine's now absent. So if they ask you for the test for an alkene, I'll really spell it out for you. If they ask you for a test for an alkene, or to prove that something is unsaturated, because after all that's really the same thing, add bromine water and you should see a colour change, which is from orange to colourless. If it goes from orange to colourless, you know you've got an alkene. Let's practice naming them. That's ethene, bromine. Because you've got 2 bromines attached, you need to put di. Di means 2. Dibromoethane is your product. It's changed to ethane because you've no longer got the double bond. So where do all these hydrocarbons come from? They come from crude oil, which contains a mixture of hydrocarbons. Crude oil is a black sticky substance obtained from the Earth's crust, but how do we turn crude oil into useful substances which make great fuels? Well, we need to carry out fractional distillation. So the first step in fractional distillation of crude oil is to heat the crude oil until it vaporizes. We pass that vapor into a fractionating column or fractionating tower. The vapor rises, cools and condenses, turning back into a liquid. There's a temperature gradient within the fractionating tower, meaning that it's hottest at the bottom and coolest at the top. That means that the fractions of crude oil, fractions just refers to compounds with similar boiling points, the fractions of crude oil with the highest boiling point will condense at the bottom where it's hottest. Fractions with the lowest boiling point, so the shortest chains, will condense at the top where it is coolest. They could ask you to list the fractions in terms of where they condense. So if we start at the top, we have refinery gases, which are used in central heating and bottled gas. Then we have petrol or gasoline, which is used as fuel for cars. Following on, we have kerosene, used as fuel for planes. Diesel oil, used as fuel for lorries and buses. Fuel oil, used as fuel for ships, and then lastly a black sticky substance known as bitumen that can be used in road surfacing and roofing materials. If we compare the various properties of the fractions, you'll find that the most volatile, the ones which turn most easily into a gas, will appear at the top, so the refinery gases. The most viscous, so the stickiest fractions, will appear at the bottom of the fractionating column. For example, bitumen. As you go down the column, the fractions get darker in colour, they ignite less easily, they have higher boiling points. So you do need to be prepared to compare these sorts of properties for various fractions within the fractionating tower. Remember that a fuel is simply a substance which releases energy when burnt. But how are we burning that fuel? Well, there's two types of combustion you need to know about. The first one is complete combustion. This involves a plentiful supply of oxygen and means that carbon dioxide and water are produced. This is a favourable situation. You want complete combustion to occur. Incomplete combustion refers to when there's an insufficient amount of oxygen present, and as a result, carbon monoxide, water and carbon can be produced. Carbon is effectively soot, which causes global dimming. Carbon monoxide is a major issue because it's a toxic gas. Remember, what it does is it combines with the hemoglobin in our red blood cells in our blood, preventing them from transporting oxygen. This can lead to suffocation. Other environmental issues include the fact that high temperatures in car engines can cause the usually inert, unreactive nitrogen and oxygen gases present in our atmosphere to react. They form nitrogen oxides, which when they dissolve in rainwater can form acid rain. A second source of acid rain is the sulfur impurities found in crude oil. When these are burnt in our cars, they react with oxygen in the air to form sulfur dioxides. These again can dissolve in rainwater, forming acid rain. Acid rain is an issue because it damages limestone buildings, it damages trees, and it makes our lakes and rivers too acidic for the aquatic organisms that live there. Sometimes we like to break down our hydrocarbon chains further in a process known as cracking. Cracking involves taking long hydrocarbon chains and breaking them down into smaller, more useful chains consisting of a mixture of alkanes and alkenes. Remember, alkenes can be used to make plastics. Cracking is an example of a thermal decomposition reaction, which means breaking apart a substance using heat. The conditions you need for cracking include a temperature of 600 degrees Celsius and an alumina or silica catalyst. There are three isomers with the molecular formula C5H12. One of these isomers is pentane. This is its displayed formula. What is meant by the term isomers? Compounds with the same molecular formula, but different displayed formula. Draw the displayed formula for another isomer of C5H12. So I'm going to make it branched, so I need to reduce the number of carbons in the main chain. I'm going to bring one off here, and then I'm going to complete with hydrogens, make sure that each carbon atom has 4 bonds, each hydrogen has 1 bond. And it's so important that you double check your molecular formula to make sure you've actually got an isomer. So is this still C5H12? Count them. 1, 2, 3, 4 carbons, yes. What about the number of hydrogens? 3, 6, 7, 8, 9, 10, 11, 12. Yes, I'm happy I've obeyed C5H12. Pentane reacts with bromine in the presence of UV light. Complete the equation for this reaction. So I know straight away that this is a substitution reaction because we've got an alkane reacting with bromine. So as a result, I'm going to make HBr as my byproduct and C5H11Br as my main product. Double check that your number of atoms for each element add up on the left and right side of your equations. This question is about octane, which is produced in the gasoline fraction during the fractional distillation of crude oil. That's the same as the petrol fraction. It's just a kind of more American way of saying it. The diagram shows a fractionating column. Describe how crude oil is separated into fractions. So we want to heat the crude oil until it vaporizes, pass the vapor into the fractionating column. Longer chains condense at the bottom where it's hottest. Octane can be also produced by the process of cracking. Give the conditions for cracking, so we need a very high temperature of around 600 degrees and an alumina catalyst. Synthetic polymers, so really we're talking about how we make plastics. A couple of definitions to kick things off with. So first of all, what is a monomer? It's a small molecule that joins together to form a polymer. What is a polymer? It's a long chain formed from many small molecules, monomers, joined together. So you can see these terms are very tightly linked. We want to look at addition polymers. So I'm going to show you how we're going to form the plastic polyethene from ethene monomers. So according to our definitions, we're going to join lots of our ethene monomers together in order to form a polymer polyethene. And after all, poly means many. So we've got many ethenes joined together. So here's ethene. It's its displayed formula. If they ask for an equation showing the formation of polyethene, what you want to do is break the double bond, elongate the bonds, add your hydrogens back in, and include square brackets. You also write an N to show that you've got many of these ethene monomers joining together. So as I said, here's your monomer and here's your polymer. If they ask for the repeat unit, your repeat unit simply looks like the polymer but without the square brackets and the N. So this is your repeat unit. Now, polyethene is a useful substance because it can be used to make cling film and plastic bags. It is your archetypal plastic. Now we're going to take propene, our monomer this time, and we're going to form polypropene, which is a polymer. Let me show you the equation for its formation. Obviously, propene we usually draw like this, but to make it so much more straightforward in your equation, I want you to write it like this. It is exactly the same thing, but it'll be much better if you write it like that. But you've still got C3H6. So let's clear this out of the way so you can see it nice and clearly. Just be very mindful when you draw these bonds. People have a habit of drawing that bond in between the carbon and the hydrogen. No, the bond is formed between the 2 carbon atoms, so show that. Then to show the formation of polypropene, again we break the double bonds, we elongate the bonds, we add in our atoms again, Include your square brackets and the N. So here's propene, this is polypropene. If they ask you for the repeat unit, again, just remove the square brackets and the N. This is your repeat unit. Now, polypropene is a harder plastic compared with polyethylene. It's used to make buckets, plastic water pipes. Let's take another monomer, chloroethene. And I want to make polychloroethene. So we have a C double bond C as our monomer. We have hydrogens, but because of the chloro, we've got one chlorine atom. Break the double bond, elongate the bonds, include all the atoms again. Include square brackets and an N. And you're going to be using polychloroethene to make window frames. Now we're going to take tetrafluoroethene. The polymer we're going to make is polytetrafluoroethene. Let's draw it. So there's the ethene, tetra meaning 4. It means we've got 4 fluorine atoms attached. Break the double bond, elongate the bonds, add your fluorine back in, square brackets and an N. Now polytetrafluoroethene is used as non-stick saucepan coating, so you might have heard of it being called more commonly Teflon. Now these are all examples of addition polymers. Addition polymers are really hard to dispose of, and the reason for that, as with so many plastics, is because they are non-biodegradable. Biodegradable refers to the ability of a substance to be broken down using microorganisms. So obviously in this case, microorganisms can't break down the addition polymers. So as a result, they occupy landfill. You can try and burn these plastics, but unfortunately they'll release toxic gases when burnt. The diagram shows the displayed formula of chloroethene. State why chloroethene is described as an unsaturated compound, because it contains the carbon-carbon double bond. Describe a test to show that chloroethene is unsaturated. This is when we add bromine water, and we should see a colour change of orange to colourless. Name the polymer formed from chloroethene. Let's draw it here. Break that double bond. Check what you've got. Polychloroethene.